Hello, my dear students. I hope you all are really doing great. First of all, I welcome you all on this PW English channel. Students, as per your demand, now we are here with complete JEE Mains and NEET series. Talking about chemistry, student, the course flow will be like this. First, we will start with organic chemistry. Then we'll move towards class 11th physical. Then we'll move towards class 11th inorganic. Then we'll move towards class 12 physical, and at the end we'll complete this chemistry syllabus with inorganic. So this will be the course flow of chemistry. Talking about today's lecture, today we'll start one of the most important topic of organic chemistry, that is general organic chemistry. So today we'll be talking about GOC. The next lecture will be all about isomerism, and the third lecture will be reaction mechanism. Talking about today's lecture, today we'll start with electronic effects, that is inductive effect. Then we'll move towards resonance. Then we'll move towards hyperconjugation, concepts of aromatic compounds, aromaticity, anti-aromaticity, non-aromaticity. Then we'll move towards concepts of acids. Student, the concept of base we'll be doing in lecture 3rd. Whenever we are going to do reaction mechanism in that particular lecture, we can say in lecture 3, we'll start lecture 3 with concept of base, that is the comparison of basic strength of organic compounds, and then we'll move towards the reaction mechanism. So without wasting any further time, let's start our discussion. The first effect, inductive effect. The first electronic effect which we are going to study today is inductive effect, right? Can you tell me how do we define it? Student, it can be simply defined as whenever any atom or group are connected to a carbon chain, there is polarization, there is partial polarization, in chain due to sigma electron transmission. And this particular effect, is referred as or is called as inductive effect. Whenever any atom or group is connected to a carbon chain, there is polarization in the chain, and this polarization is mainly because of the sigma electron transmission, right? And this particular effect is referred as inductive effect. So students, till yet mainly we have learned what is inductive effect. It's nothing but polarization in chain due to sigma electron transmission. Now let us try to understand how it is measured. It's always measured with respect to hydrogen atom. How? Let's try to understand it with the help of one example. I'm going to take 3 carbon chain C, and here it is connected to a group hydrogen itself. Okay, I'm having C, here it's connected to Z, and I'm having one more carbon chain C, and here it's connected to G. Okay, I'm having 3 carbon chains. The group here is hydrogen. This carbon chain is connected to hydrogen. It is connected to a group Z, and the last one is connected to a group G. Now what I am going to do, I am going to measure the electron density. Okay, let us assume the electron density induced in this carbon chain because of hydrogen is X. X is the electron density induced. Okay, because of this group Z, The electron density induced in this carbon chain is, let us assume it is Y. Okay, the electron density in chain 2 is Y, whereas the electron density in chain 1 is X. Okay, the electron density induced in chain 3, let's assume it is Z. Now let's discuss some cases. Okay, let us assume the electron density in chain 1 is greater than that of 2, means X is greater than Y. If X is greater than Y, what does this mean? Basically it means here the electron density is more as compared to this group. So can I say this group Z is basically trying to pull out the electron cloud from the chain? This group Z is trying to pull electron from the chain, right? Because of this pulling of electron from the chain, can I say the first carbon atom will get somewhat delta positive, right? And it will get some delta negative, right, student? Now, if I focus in the entire chain, let's assume it is carbon 1, carbon 2. Now, with respect to carbon 2, carbon 1 is more electronegative. So, can I say now here, there will be polarization in carbon 2 also. Carbon 2 will also get somewhat delta positive. Similarly, now if I compare carbon 2 and carbon 3, can I say carbon 3 will also get induced? Although the magnitude of induction will be somewhat less, right? And similarly, this one will also get induced, right? So can I say this group Z, which is trying to pull out the electron, and because of this pulling of electron, the electron density in the chain is getting reduced. Such a group which basically tries to pull out the sigma electron cloud towards itself is referred as minus I group. Minus I group. Right? Now let's take one more case. Let us assume Z is greater than this Z. The electron density Z is greater than X. What does this mean? Basically, it means the electron density in chain 3 is greater than that of 1. It simply indicates that the group G is trying to release or push electron cloud into the chain. Right? There is a tendency of this group G to release sigma electron cloud towards this chain. Because of that, can I say this carbon will get somewhat del negative? Now, because it's receiving electrons, sigma electron clouds, right? Now, since this sigma carbon is having a del negative, obviously the electron cloud will have a tendency to move towards the carbon 2. Why? In order to avoid interelectronic repulsion. Because of that, this one will also get somewhat delta negative. Again, in order to avoid interanionic repulsion, the electron clouds will move towards carbon number 3. This one will also get somewhat delta negative. And this one will also finally get somewhat delta negative. And this one will get delta positive. So student, the group which basically releases or pushes the sigma electron cloud into the chain is referred as plus I group, plus inductive effect. Whenever in GOC, whenever I mention plus, it's simply electron releasing group, electron donating group. It can be sigma electron donating group. It can be through sigma electron transmission, or it can be through pi electron displacement. But plus group always electron donating group, whereas minus is always EWG, electron withdrawing group. Okay, so here Z is electron withdrawing group, so it will be referred as a minus I group, and G is the electron releasing group, will be referred as plus I group, right, student? So this is how we measure inductive effect, and it's always measured with respect to hydrogen atom. Third most important point, it is a distance dependent effect. Obviously you can see here I will have maximum polarization because this carbon is directly connected to the chain, but with increase in the distance, the polarization or the intensity of polarization will get somewhat reduced, because this carbon will have somewhat less delta negative as compared to the carbon 1, right? So inductive effect is purely a distance dependent effect. Fourth important point, it's a permanent effect, right? It's not that some species is attacking, so for a certain time there is polarization. No, the polarization is observed always, right? So inductive effect is a permanent effect. Once again, I am repeating all the points related to inductive effect. First, the polarization in chain. Whenever any atom or group of atom is connected, this particular effect is referred as inductive effect. It is mainly due to sigma electron transmission. Second, it's always measured with respect to hydrogen atom. So we are having two inductive groups, minus I group and plus I group. Plus I electron releasing group, minus I electron withdrawing group, right? Third one, it's a distance dependent effect. Obviously, with increase in distance, the intensity will get somewhat reduced. Fourth, it is a permanent effect. Now students, it's time to discuss this minus I group first of all. Inductive effect or minus I effect. Already I have told you, the group which basically withdraws the electron cloud is referred as minus I group. Which all group will have a tendency to withdraw or will have a tendency to polarize the sigma electron towards itself? Can I say all the electronegative species? Right? Even the electron deficient species. Can I say all the cationic species will act as a minus I group? All the cationic group, they are the electron deficient species, will have a tendency to pull the sigma electron cloud towards itself. Because of that, the electron density in chain will reduce, right? Okay, so all the cations will behave as minus I group. Can I say electronegative elements have a tendency to pull out the electron towards themselves? So can I say all the electronegative elements like halogens, FCl, Bri, they all will act as a minus I group, right? So generally the electronegative elements and all the cationic elements behaves as minus I group. Now it's time to discuss the relative order of some of the minus I groups. Okay, students, here I have told you, generally the cationic species are highly electron deficient species. So they always have a tendency to pull out electron cloud towards themselves. So all these Nr3 positive, Sr2 positive, NS3 positive, even one more species is there, NF3 positive. They all will act as a minus I group, strong minus I, right? Apart from this, we have some neutral species like nitro, sulfonic, cyano, aldehyde. They all will also behave as a first cation, then nitro, cyano, sulfo, aldehyde, acid, right students? Then we have halogens. Then we have one more interesting point. We will discuss it, don't worry. OR and OH, right? One alcohol group and one ethyl group. They also behave as a minus I group. Then we have NH2. Now why NH2 is less as compared to OH? Simple electronegativity. Oxygen, more electronegative, will have a higher tendency to pull out the electron cloud towards themselves. Then we have alkyne. Here the percent S character is 50%. So electronegativity is very high, and because of that it will have a tendency to pull out electron cloud, right? Okay. Then I will have phenyl. sp2, all atoms are sp2 hybridized. But between alkyl and phenyl is a better minus I group. And then we will have hydrogen as a reference group. So student, cationic, then we have some neutral species or groups like nitro, cyano, sulfo, aldehydes, acids, right? Then we have halogens, FCl, Bri, then we have OH and OR, then we'll have alkynes, phenyls, alkenes, and hydrogen. If I talk about the isotopic effect between hydrogen D and T, student, this H is always the reference group. Now this D and T will act as a plus I group relatively. Rather than acting as a minus I, it mainly acts as a plus I group. Deuterium and tritium. We'll discuss that. Okay. So let's move ahead. Now moving to the next part, that is plus I. Already I have discussed, because of this the electron density in the chain will increase, right? It's an electron releasing group, sigma electron releasing group. The chain will get del negative, right? Chain will have somewhat increased electron density whenever this group is connected. So can I say all the electron rich species will have a tendency to donate, right? Whenever I am having a tendency to donate means I am rich, then only I will have a relative tendency to donate, right? So can I say all the electron rich species will have a tendency to donate sigma electron cloud to the chain. So all anionic species will act as a plus I group. Let's write this point. All anionic species will act as plus I group. Like I'm having CH2 negative, NH negative, O negative. These are the anionic species. They are the electron rich species. They will have a tendency to donate sigma electron clouds, right? So they will act as a plus I group. Apart from this, the alkyl groups, they also act as a plus I group. And after this, we will have alkyl groups only, like 3 degree maximum. 3 degree carbon is like this, right? So it will have a maximum tendency. Then I will have 2 degree. Then I will have, students, 1 degree, mainly species like this, CH3, CH2, ethyl group, right? Then I will have CT3, then I will have CD3, then I will have CH3, and then I will have T, D and H. Why tritium or deuterium is having higher electron donation tendency as compared to hydrogen? Yeah, it's mainly because if I talk about this carbon, hydrogen, carbon, deuterium and carbon tritium bonds. Okay. Because of the increased mass, the vibration is less. So here the bond length will somewhat be less. So it's very near to this carbon, right? Because of that, it will have somewhat more tendency to donate sigma electron cloud to carbon as compared to deuterium. And deuterium being higher in mass or having higher mass, here the bond vibration observed will be relatively less, and because of that it will be nearer to carbon, and as it is nearer to the carbon chain, it will have a higher tendency to donate. That's why deuterium and tritium will act as a better plus I group as compared to hydrogen. If I talk about alkyl group, 3 degree, then 2 degree, ethyl, then I will have CT3, CD3, and then I will have methyl, and the last I will have hydrogen, right? Generally, all the anionic species will have a tendency to donate sigma electron cloud, and because of that, the chain will be rich in electron density. They will have somewhat del negative, whereas the group will get somewhat del positive. This polarization in the chain is nothing but inductive effect. We have studied 2 types of inductive effect, minus I, plus I. Because of minus I, the electron density in the chain will reduce. Because of plus I, the electron density in the chain will increase. So students, till yet mainly we have learned what is inductive effect and what are the different types of inductive effect. Now, why it is so important? What are the effects of this inductive effect, what will happen to the reaction intermediate if any such groups are connected. Let's try to understand that. Let's try to understand the applications of inductive effect. The first application which is there on the screen, and that is acidic strength. How do we measure acidic strength, student? Don't worry, we are going to discuss a lot more about this acidic strength in today's lecture itself, but we'll do once we have thoroughly studied all the electronics effect. Here I will give you a brief introduction about acidic strength. If I am having a acid HA, it will dissociate as H plus plus A minus, right? Acids, arranged acids are generally having a tendency to release H plus. As soon as it releases H plus, I will have A minus. Now I am given to measure acidic strength of certain compounds. Obviously, all the time I cannot go to the lab and cannot measure Ka value and all these things. So what we can do, we have a simple technique. Whenever you are asked to measure or to compare the relative acidic strength, simply compare the stability of this conjugate A minus. More is the stability of A minus, higher will be the acidic strength. Higher the stability of A minus, the stability of A minus higher is the acidic strength. It's the acidic strength. Now let's try to see how this inductive effect will play a major role in comparing the acidic strength. Okay, I'm having a compound like this, CH3COOH. I'm having CH2F C double bond OH, and then I'm having CH2COOH NO2, right? I'm given three different compounds, CH3COH, CH2FCOOH and CH2NO2COOH. Students, the first step, remove the most acidic hydrogen. So I have removed it. I have formed the anion. Now I will check whether the anion is stable or unstable. Here this anion is connected to CH3 group. This CH3 will act as a plus I group. What this plus I will do? This plus I will have a tendency to release electron clouds. Can I say it will increase the electron density on anion? Already it's an electron rich species, and further I am giving electron to an electron rich species. Can I say the volume charge density will increase? Because of that, the potential energy will increase, right? And because of that, stability will decrease. So students, always keep it in mind. If a plus I group is connected to electron rich chain or electron rich species, stability will decrease. If a minus I group is connected to a electron rich chain or electron rich group, stability will increase. Plus I to anion decreases the stability, minus I to anion increases the stability. Plus I to anion decreases the stability, minus I to anion increases the stability. Similarly, minus I to cation already electron deficient species, and further I am trying to withdraw electron cloud from there, right? Stability will decrease. So minus I2 cation decreases the stability, plus I2 cation increases the stability. I hope you understood this fact. Let me write it. Plus I2 cation C plus increases stability. Minus I2C plus decreases stability, right? Similarly, minus I2C minus increases stability, and plus I2C minus decreases stability. Simply you need to look at volume charge density. If minus I group is connected to an anionic species, the volume charge density will decrease because the minus I will try to pull out the electron cloud, right? Because of that, the electron density on anion will decrease, and because of that, potential energy will decrease and the stability will increase, right? So student, always keep it in mind, whenever a minus I group is connected to any acidic compound, the acidic strength will increase. A plus I connected will decrease the acidic strength. Minus I group increases acidic strength. Plus I group decreases acidic strength, right? So here I'm having NO2, I'm having F, and all CS3. So can I say here complete plus I group is there? Acidic strength will be relatively less. Now between this fluorine and nitro, can I say nitro is a better minus I group? So can I say here I will have more stabilization of this anion COO minus, and higher the stability of this A minus, better is the acidic strength. So can I say third one is going to be most acidic, then I will have second one, and then I will have the first one, right? I hope you understood this acidic strength. Let's move ahead. Second point, basic strength. Student, what do we mean by the term basic strength? It's always the tendency to donate a pair of electrons, right? We'll discuss about this basic strength also later on in this chapter itself. But right now, just let's talk briefly about this basic strength. Okay. So the tendency to donate pair of electrons. And this tendency to donate pair of electrons will be maximum when the electron density is maximum, right? And can I say here, if a plus I group is connected, it will increase the electron density, and with increase in the electron density, the donation ability will increase. Whereas if a minus I group is connected, it will pull out the electron cloud, right? The electron density will decrease, the donation ability will decrease, the basic strength will decrease. So plus I group increases basic strength, a minus I group decreases basic strength. Okay, I'm taking few examples. Let's try to understand that. So now, with the help of certain examples or few examples, let's try to understand how does inductive effect impact the basic strength of a certain compounds. Okay, I'm giving you 2 to 3 examples. I'm having CS3, CH2, NH2. Okay, and here I'm having CS3, NH2, first one. Okay, next I'm having CS3, C, triple bond N, lone pair. Okay, and I'm having CS3, C, double bond NH. The last one, third one, I'm having a compound like this, NH2, and here I'm having N. Okay, let's compare the basic strength in these 3 compounds. Okay, student, if I look at the first example, here the group connected is ET. Here the group connected is Me. Between Me and ET, which one is a better plus I? Can I say more plus I? More is the plus I, more will be the electron density on this NH2. More is the electron density, higher will be the basic strength, right? Okay. Now, between these 2 compounds, The group connectase is methyl, the group connectase is methyl. But if I look at this nitrogen, it is connected to a sp carbon, right? And if I look at this particular nitrogen, it is connected to sp2 hybridized carbon. Can I say here the percent S character is 50% S character, and here the percent S character is 33%. With increase in the percent S character, the electronegativity increases, and if with increase in electronegativity, the minus I character starts dominating, right? And because of that, the basic strength will decrease. So now you can simply tell me between this cyano and this one C double bond NH, which one is more basic? Obviously this one, right? Now let's look at the third compound. I'm having NH2 and it is connected to a alkyl chain, which will act as a plus I group, will increase the electron density on this nitrogen. Because of that, the basic strength will increase. If I look at this nitrogen, it is connected to a sp hybrid carbon from all the sp2 hybrid carbon from all the sides, which is having 33% S character, so more electronegative, right? So can I say the induction will be like this? So the electron density on this nitrogen will decrease. And if electron density will decrease, the relative donation ability will decrease. Because of that, the basic strength will decrease. So these are the impacts of inductive effect on basic strength. Plus I will increase the basic strength, minus I will decrease the basic strength. I hope you understood this. We'll do a few more examples once all the applications are done. Okay. Students, moving to the third applications of inductive effect, that is dipole moment. If we look at this dipole moment, from the beginning itself, we are saying inductive effect creates partial polarization in the chain, and if there is polarization, obviously the dipole moment will get impacted, right? So inductive effect influences the dipole moment of a compound, right? Let's try to understand it. I'm having CH3 C double bond O H. I'm having CH3 C double bond O CH3, right? Okay. Now, can I say oxygen is more electronegative, so it will have a tendency to pull the electron cloud towards itself, right? So can I say here I will have delta negative, here I will have delta positive. But now this carbon is connected to two alkyl group, and this alkyl group will act as a plus I group. So what this plus I group will do, it will decrease this del positive on the carbon, right? So the polarity will get somewhat reduced. If I talk about this aldehydic group, through one side it is connected to hydrogen, on one side it is connected to alkyl. Here I will have del positive, here I will have del negative. Now I'm having an electron donating group from one side only. Here I'm having electron donating group from both the sides. So here I will have less magnitude of delta positive. Here I will have more magnitudes of delta positive. So because of this plus I only, aldehydes are relatively more reactive as compared to ketone, because here I'm having more delta positive observed here, more electron deficiency observed in case of aldehyde, and because of that any electron species will easily attack here as compared to ketone. So yes, dipole inductive effect plays a major role in impacting the dipole moment of a compound. Higher is the electronegativity difference, more will be the del positive and del negative, and because of that the dipole moment will increase. Let's move ahead. The most important impact or application of this inductive effect is stability of reaction intermediates. Students, we have certain reaction intermediates, and reaction intermediates are those species which are basically produced during the progress of reaction and gets consumed totally before the reaction gets completed. We have certain reaction intermediates like carbocation. In organic chemistry, we will have free radical, we will have carbanion, then carbene, nitrene, all these things are there. We'll do one by one. Right now, we are going to discuss about these three species: carbocation, free radical, and carbanion. If I look at this one, electron-rich species, electron-rich species. If I look at these two, 6 electronic species, 7 electronic species, octet incomplete, right? Octet incomplete. And if octet is incomplete, what? It's basically electron deficient species, right? Now, what will be the impact of inductive effect on these reaction intermediates? Student, if a plus I group is connected to these two species, the yellow boxed species, plus I group. These species are the electron deficient species. Electron deficient species. Plus I connected to an electron deficient species will release the electron density in the chain, and because of that the stability will increase. So whenever a plus I group is connected to carbocation or free radical, stability increases. Stability increases, right? If a minus I group is connected to electron deficient species like carbocation or free radical, already free radical or carbocations are the electron deficient species. They are in need of electron, and still if I am trying to pull out the electron cloud, what will happen? The volume charge density will increase, the del positive will increase. Because of that, the potential energy will increase, stability will decrease. So a minus I group decreases the stability of electron deficient species like carbocation and free radicals. Even we are having certain species like carbines, nitrines, but we'll talk about them later on. If I talk about carbanion, electron rich species, I'm having carbanion. This is the electron rich species. Now to this species, if I am adding plus I group, plus I, what will happen? The volume charge density will increase. The plus I will still release the electron to this carbanion, already electron rich, and further I am increasing the electron density. The volume charge density will increase, the potential energy will increase, stability will decrease. So plus I to electron rich species decreases stability. Minus I to electron rich species, minus I is connected to electron rich species, increases stability. Right, student? Okay. Students, in 1 minute, let's summarize all the applications of inductive effect. Talking about acidic strength, minus I will increase the acidic strength, plus I will decrease the acidic strength. Talking about basic strength, plus I will increase the basic strength, minus I will decrease the basic strength. Talking about stability of reaction intermediates, most important, electron deficient species will get stabilized by plus I, electron rich species will get stabilized by minus I. Let me write that. Plus I, what it will do? Increases basic strength, increases the stability of electron deficient species, electron deficient species? Like, what are the electron deficient species in general? I'm having carbocation, free radical, like that, right? If I talk about minus I group, minus I, what it will do? Increases acidic strength, right? If I talk more, then it will increase the stability of anionic species. Anionic species, as for example, I can have carbanion, electron rich species, right? So these are the certain impacts or applications of inductive effect. Let's practice few more questions and then we'll move to other electronic effects. Students, now it's time to discuss few more questions so that you have a clear-cut idea on this inductive effect. So let's start our discussion. The first one. Here I need to compare the acidic strength of compound. We need to compare Ka values. Which one is more acidic? I'm having a 3-member cyclic ring that is connected to carboxylic acid, 4-member cyclic ring and a 5-member cyclic ring. Student, now you will say, sir, how do we compare all our alkyl group, right? Now, student, in general, a strained ring behaves as a minus I group. A strained ring behaves as a minus I group. Strained ring behaves as minus I. Okay, so I'm having a 3-member ring and 4-member ring. Which one is a more strained ring? 3-member cyclic ring. So it will be a better minus I group, and minus I group increases the acidic strength. So between this one and the 4-member cyclic ring, cyclopropane carboxylic acid and cyclobutane carboxylic acid, which one is a better acid? Cyclopropane carboxylic acid. As compared to 5-member, 4-member is more strained, so better minus I. So this one will be the relative acidic strength. I hope you understood this question. Always remember, a strained ring behaves as a minus I group. Let's move ahead. Next one. I'm having 6-member cyclic ring connected to carboxylic acid, carboxylic acid, carboxylic acid. Once again, I need to compare the acidic strength of the compound. The group connected is chlorine, acts as a minus I group. Fluorine acts as a minus I group. Between chlorine and fluorine, fluorine is a better minus I, no doubt. And here I am having bromine, 2 bromine, right? Okay, so 2 minus I group. I need to compare the acidic strength. Student, no doubt fluorine is having maximum I as compared to chlorine, bromine and iodine. But then we'll look at the distance also. Okay, here fluorine is present at 1, 2, 3, 4, 4th position. At 4th position, or 4th carbon, from 4th carbon onwards, the relative intensity of inductive effect decreases. So here fluorine won't have a stronger minus I impact as compared to chlorine, which is nearer to the group, right? Now, if I look at chlorine and bromine, no doubt chlorine is having a stronger minus I, but 2 weak minus bromine group will dominate over 1 single chlorine group. So 2 weak minus I group dominates over a relatively strong single minus I. So which one is going to be more acidic? Third one. Then I will have first one, and then I will have second one. Once again I am saying, first, between fluorine and chlorine, because of distance, fluorine will have a weaker minus I as compared to chlorine. If I compare between chlorine and bromine, 2 weak minus I will create a strong impact as compared to 1 minus I. So the relative order goes like this: 3, 1, 2. Okay, now let's move to the third compound. I'm having 1 degree carbocation. No doubt plus I group, so Because of the induction, the volume charge density on this carbocation will decrease, stability will increase, right? But it's a 1 degree, it's 3 degree. From all the sides, this carbocation is getting stabilized. A 3 degree radicals or 3 degree alkyl will have a better plus I as compared to 1 degree or 2 degree. So it's a 3 degree. If I talk about this carbocation, it's a 2 degree carbocation. Which carbocation will be more stable? First, it is going to be 3 degree, then 2 degree and 1 degree. The relative order goes like this. I will have second, then I will have third, and then I will have 1. 3 degree, 2 degree and primary carbocation. This is all about the stability of carbocation. Let's move ahead. Now here we need to check the stability of carbanion. A carbanion gets stabilized by minus I group. Here I am having ethyl which will act as a plus I group, and this plus I group will increase the volume charge density on carbanion. Because of that, the stability will decrease. Plus I always decreases the stability of anion. Here I am having fluorine acting as a minus I. If I compare between 1 and 2, can I say this carbanion will be relatively more stable? Right? Now let's compare between 2 and 3. Here fluorine is connected to carbon 2. Fluorine is connected to carbon 3. Inductive effect is a distance dependent effect. Lesser the distance, stronger the impact. Lesser the distance, stronger the impact. Here the impact will be more stronger as compared to the third one. So can I say second is more stable? Then I will have third and then first. The last one. Here I am having alcohol, right? Cyclohexanol, no phenol. Phenol it's not there, students, because phenol right now you can't do. So I'm having alcohol only. Okay, and then we need to compare the relative acidic strength of these alcohols. We'll simply check on the basis of minus I and plus I. Here this alcohol is connected to alkyl group, right? And one nitro group, minus I. Can I say this nitro is at carbon number 4? 1, 2, 3, 4 at very last distance, so the impact will be relatively less. Okay, let's move to the next one. Alkyl from this side, but strong Nr3 positive from this side will act as a minus I, right? So the electron clouds will get polarized towards this Nr3 positive. The minus I increases the acidic strength, and it's at carbon number 2. It's very nearer to this alcohol, so it will have a strong impact on this OH, right? Okay, I'm having NHR2 positive. It is also a stronger minus I, and the last one NH3 positive, also a stronger minus I. Now between these three, which one is a stronger minus I? Nr3 positive, strongest one. Then I will have NH3 positive. The twist in the story is, then I will have NH3 positive and then NHR2. Here it is believed in NHR2 I am having 2 alkyl group, so it will decrease somewhat positive charge on nitrogen. The electron deficiency will decrease. Because of that, the minus I impact will decrease. You can say, sir, in Nr3 positive 3 alkyl groups are there, so it should have even less minus I as compared to NH3 positive and NHR2, but it's at the strongest one. Why? Here, students, it can be answered on the basis of bond angle. Let's try to see that also. I'm having R. R is a bulky group, right? Can I say because of that the bond angle will increase? Theta will increase. With increase in the bond angle, can I say the percent S character will increase? Right? And with increase in the percent S character, can I say electronegativity will increase? right? So Nr3 positive will have strongest minus I, then I will have NH3 positive, and then I will have NHR2. Now the question is very easy. Second is going to be the most acidic, then I will have 1, 2, 3, fourth one, then I will have third one and first one. Anyhow, a cationic species acts as a better minus I as compared to the neutral one. I hope you understood it. So students, this was all about inductive effects. It's moving to the second electronic effect which is there on the screen, and it's resonance. Let's try to understand what do we mean by the term resonance, a highly important subtopic of GOC. Let's start our discussion. Resonance can be defined as the delocalization of pi electron components in parallel p orbital. First, let me write it, then I will explain each and every point. Delocalization of pi electron component in parallel p orbital. Okay, now you will say, so what do we mean by the term delocalization? It's nothing but movement. So delocalization, if I define one by one, this delocalization is nothing but movement. So movement of pi electron, which all species are treated as a pi electron component. Let me write that first of all. Negatively charged species, then I will have species containing unshared pair of electron, or we can say lone pair, double bond, then we will have free radical and positive charge. They are basically treated as pi electron components. Okay, so the movement of these electronic species, where this movement will occur? In parallel p orbital. Now what do we mean by the term parallel p orbital? Let me explain that also. I'm having a compound like this, CH2, doubly bonded CH, singly bonded CH, doubly bonded CH2. Can you tell me the hybridization of each carbon here? Can I say all the carbons are sp2 hybridized? sp2, sp2, sp2 and sp2. So can I say in all carbons I am having a p orbitals which has not participated in hybridization, that's a pure p orbital, and that will lie perpendicular to the plane, because two p orbitals are used in hybridization. So one which has not participated in hybridization, which is totally pure, will be perpendicular to the plane. So I'm having a pz. So obviously this one will also have a pz p orbital, pz. So can I say these p orbitals, these pure p orbital, pz, pz, pz's, can I say that they are parallel p orbitals? So now can I define resonance? The movement of these electron clouds in these orbitals. Movement of pi electron components in parallel p orbital is nothing but resonance. Now you may say, from where to where this flow will occur, right? Either whether the flow will occur from positive to negative or from negative to positive. Student, we have studied in physics, the movement is always from high potential to low potential. If I leave this pen, obviously it will drop. Why? In order to increase the stability, the potential energy will decrease, right? So here the movement will occur from high potential to low potential. High potential to low potential. So the movements of pi electron component in parallel p orbital from high potential to low potential is nothing but resonance. I hope you understood what do we mean by the term resonance. So students, moving ahead, the second question which may strike your mind is, will all the organic compound exhibit resonance? The answer is no. Only certain organic compounds which is having pi electron components, which is having planarity, will exhibit resonance. Let us try to understand it with few examples. I'm having a molecule like this, CH3 CH doubly bonded CH2. Will it exhibit resonance? Tell me. The answer is no, it will not. Why? For resonance to occur, at least 3 carbons or 3 consecutive carbons, minimum 3 consecutive carbons has to be either sp2 hybridized or sp hybridized, means it has to be planar. What's the hybridization here? sp2, sp2. But the third one is sp3, right? So obviously the pi electron component will not flow here. It's not a parallel p orbital. It's not finding any parallel p orbital, right? So no resonance. Will resonance occur here? Will resonance occur here? Yes, here resonance will occur. How? Let's see. sp2, 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 sp2. All carbons are sp2 hybridized, right? So every carbon is having a parallel p orbital. It is having a pi electron component, that is double bond. Resonance will occur here. Okay. Third one. Will resonance occur here? What I have told in the beginning, for resonance to occur, at least 3 consecutive carbons has to be sp2 hybridized. sp2, 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 2, 2, sp3, sp2, sp2. You will say, sir, here 4 carbons are sp2 hybridized, but it's not 4 carbon, or it's not the number of carbon. It's basically the minimum 3 carbon or the minimum 3 consecutive carbon has to be sp2 hybridized. Here only 2 carbons are, or 2 consecutive carbons are sp2 hybridized. No resonance. Right, students? Let's move ahead. Let's talk about this one. I'm having CH3, CH2, CH2 negative, and one more case, CH2, CH3, CH doubly bonded CH, CH2 negative. Okay, let us try to understand resonance in these two compounds. Okay, can you tell me the hybridization of each carbon here? It's sp3, sp3, and what's the hybridization of this carbon? 1, 2, 3, and 1 this negative charge. Steric number 4 hybridization is going to be sp3. Perfect. Is there any pi electron component here? Not at all. Now, so will resonance occur here? No resonance. Okay. Now let's have a look at this one. Hybridization sp3. So will this carbon participate in resonance? No. But whether this molecule will participate in resonance, that we need to check. Okay. What's the hybridization here? sp2. sp2. What is the hybridization here? Just now I had told this carbon ion is sp3 hybridized. So whether this one will also be sp3 hybridized? Whether it will be sp3 hybridized or sp2 hybridized? Tell me fast. It will be simply sp2 hybridized. Now the question is why? Why? The answer is, whenever any atom containing negative charge or a pair of lone pair, whenever any atom containing negative charge or unshared pair of electron, or you can say lone pair, is a neighbor of sp2 hybridized carbon, then this negative charge is treated as a pi electron component. Students, pi electron component does not participate in hybridization, right? So what is going to be the steric number? 1 and 2, 3. Steric number is 3. Hybridization will be sp2. This negative charge will be treated as pi electron, right? So if carbanion is connected to a sp2 hybrid carbon, sp2 hybrid carbon, that carbon ion is sp2 hybridized. If carbon ion is connected to sp3 hybrid carbon, then it is sp3 hybridized. There no movement. This carbon ion is treated as, this negative charge is treated as sigma electron, whereas this negative charge or unshared pair of electron will be treated as pi electron component, right? So here the hybridization is sp2. Now whether it will participate in resonance, sp2, sp2, sp2. I'm having 3 consecutive carbons which are sp2 hybridized. Yes, resonance will occur here. Let's take few more examples. I'm having CH3, CH2, or let me draw it like this. CH, doubly bonded CH. Okay, and then I'm having CH2 positive. Perfect. Whether this one will exhibit resonance? Let me check. Okay. If I talk about this terminal carbon, sp3 hybridized, it will not participate in resonance. This one won't participate. Here, sp2. Alkenes are always sp2 hybridized. sp2. And let me tell you one more thing. Carbocation, carbon bearing positive charge, always sp2 hybridized. Always sp2 hybridized. So I'm having 3 carbons which are conjugative, will participate in resonance because all these 3 carbons are sp2 hybridized. Planarity is there, conjugation is there, so I will have resonance, students. So here also resonance will occur. I hope you understood which all compounds will exhibit resonance. For resonance to occur, pi electron component has to be there, and second, conjugation or planarity has to be there. If the molecule is planar, if it is having a parallel p orbital, if it is having a p orbital vacant, resonance will definitely occur there. I hope you understood it. Let us move ahead. So students, now we have understood what is resonance, what are the conditions of resonance. Now it's time to learn how do we draw resonance, right? And most important, while drawing resonating structure, what are the different rules which we need to keep in mind? The first one, students, while drawing resonating structure, we have to keep it in mind only pi electron movement occurs. There is no movement of sigma electron component. While drawing the resonating structure, we have to keep it in mind only pi electron component moves. There is no movement of sigma electron. Let me try to explain it with one example. I'm having CH2 doubly bond CH, CH doubly bond CH2. Now you can say whether this molecule will exhibit resonance or not. Yes, it will exhibit. But if someone draws like this, CH2, CH2, and then doubly bonded CH2. What he has done, he has moved one of the sigma bond, right? So will it be a valid resonating structure? Not at all. So it is not going to be a valid resonating structure. Let's move to some more rules. While drawing resonating structure, there is no movement of atoms. Only the movement or the delocalization of pi electron component occurs. Let's try to understand it. I'm having a compound like this, CH doubly bond CH single bond CH doubly bond CH2. Now what a student does, he basically writes it like this, CH3 C doubly bond C doubly bond CH2, and here I'm having one hydrogen. If I look at these two molecules, the number of pi bonds are same. But if I look at this one, here on carbon number 2, 1, 2, 3, 4, 1, 2, 3, 4. So here from carbon number 2, basically what he has done, he has moved one hydrogen atom to carbon number 4 in this structure. So will it be a valid resonating structure? The answer is big no. While drawing resonating structure, we have to keep it in mind. the atoms are not moved. There is no movement of atoms. So not a valid structure. Right, student? While drawing resonating structure, we have to keep it in mind there is no movement of atom, only the delocalization or the movement of pi electron will occur. I am repeating it n number of times so that it finally settles to your brain. The number of paired electrons are same and the number of unpaired electrons are same in two resonating structure. While drawing resonating structures are also referred as canonical. So the two canonicals should have the same number of paired and unpaired electrons. Let's try to understand it. I'm having CH2, CH, CH, doubly bond CH2. What one student does, he breaks this double bond CH2, he write it like this, CH, double bond CH and single bond CH2. Will it be a valid resonating structure? Will it be a valid resonating structure? The answer is no. It won't be a valid resonating structure. Why? Here, if I look at this molecule, I'm having 2 pi bonds, 4 pi electrons. Here, 1 pi bond. At the same time, I'm having 2 unpaired electrons. 2 unpaired electrons. Right? The number of unpaired electrons in these two compounds or in these two structures are not the same, so they are not the canonicals. Not the canonicals. Canonical structures or canonicals are also referred as conjugates. Right? So they are not the conjugates. Resonating structures are called canonicals, or we say it as conjugates. So these two structures are not the conjugates. Let's move ahead. Octet rule is not violated for second period element. Why? Because second period element does not have a vacant d orbital so that it can accommodate the additional electrons. Right? So we cannot have expanded octet for second period elements. From third period elements, definitely we can have, but for a second period element, we cannot have. Let's try to understand this with one more example. I'm having a structure like this. CH2 doubly bonded CH and it's 3 positive. Okay. Now what a student does, he simply moves this pi bond to this carbon here and he draws like this. CH2 positive, CH doubly bonded NH3. Will it be a valid canonical or conjugate? Tell me. The answer is big no. Here nitrogen covalency will be 5. Nitrogen cannot have a covalency of 5, or here I can have 10 electrons here. 5 bonds, 10 electrons. So this canonical cannot be accepted because nitrogen does not have a vacant d orbital so that it can accommodate the additional electron component, right? So it's not going to be a valid structure. Not a valid structure, right? So we cannot have expanded octet for a second period element. Let's move ahead. Students, generally high energy canonicals are ignored. Only those canonicals are accepted or accepted where the energy is comparable, right? So these are the certain rules which we have to keep it in mind while drawing resonating structure. So now we have studied what is resonance, what are the different conditions for resonance, right? What are the rules that we have to keep it in mind while drawing resonance. The next one, what are the different types of resonance? That is the types of conjugation. Let's move to that one. Types of conjugation. Okay, let's start that. Double bond conjugation. Double bond double bond conjugation. Okay, I can have a structure like this. Okay, let's try to understand it. What is the hybridization of each carbon atom? sp2, right? All carbons are sp2 hybridized. So will resonance occur? The answer is yes. Resonance will definitely occur. Now, how does the flow will occur? Or it's a double bond, double bond. Every pi electrons are having the same potential. So, in which direction the flow will occur? The flow will occur, or the flow can occur through any direction, either from left or from right, because here I'm having only double bond and they are at the same potential. I can do anything. Let's do the flow from left. So if it will move, like, what will happen? This double bond will shift to the neighboring carbon. As soon as it shifts to the neighboring carbon, this carbon will have 5 bonds, right? And carbon cannot have a covalency of 5. So what will happen? This bond will shift to the adjacent atom. So I will have a structure like this. First one. Now, can I see if it is carbon number 1, 2, 3, 4, 5 and 6? Carbon 1 will have deficiency of pi electron, so it will get a positive charge. Carbon 2, initially also it was sharing and now also it's sharing. So carbon 2 and 3, right students? Initially also it was having pi electron, 3 also having pi electron. Now, if I look at 3 and 4, can I say entire pi electron component has moved to carbon number 4? So can I say carbon 4 will have negative charge? And like this, right student? Okay, can we have one more resonating structure? Definitely. Let's try to draw that also. Negative, neighbor of sp2. So this carbon is also sp2 hybridized. Now double bond. Between negative charge and double bond, negative charge is at high potential. So the flow will occur from negative towards double. And as soon as it shifts here, this pi bond will shift on this particular carbon atom. So I will have a resonating structure like this. Negative over here, right students? Complete pi bond over here, a complete pi bond over here, and a positive over here, right? So these are the 3 different canonicals or conjugates of this particular resonance. Now let's draw the resonance hybrid. Okay. Initially the pi bond was between carbon 1, 2, 3, 4 and 5, 6. In conjugate 2 or canonical 2, it's between 2, 3, right, and 5, 6. And in canonical 3, it's between 2, 3 and 4, 5. So basically there is distribution of pi bond throughout the molecule. So can I say the pi bond will uniformly get distributed on each carbon? So each carbon will have a partial double bond character. Because of that, every carbon will have the same bond length, right? Now, carbon 1 is having positive charge. Carbon 4 and carbon 6, the negative charge is distributed. So carbon 4 and carbon 6 will have a partial negative charge, right students? So this was all about the conjugates double bond conjugation. Students, continuing with this double bond conjugation, let's take one more example and try to understand the flow of electrons. Okay, I'm having a molecule benzene carbaldehyde. Can you tell me the hybridization of each carbon here? All the carbon atoms present here are sp2 hybridized, right? All the carbon atoms are sp2, and all the 6 carbon atoms in the ring is also sp2 hybridized. Talking about this oxygen, also sp2 hybridized itself. Okay. Now, till yet we had discussed a case where there was no electronegativity difference. So in that case, the flow of electron may occur on either side, either from left to right or from right to left, right? Just now we had discussed that case. Now here, oxygen is relatively more electronegative as compared to carbon. In a double bond conjugated system, if one of the atom is participating in resonance and if it's more electronegative, the flow of electron always occur towards more electronegative element. The flow of electron, the flow of pi electron will always occur towards more electronegative element, more electronegative element. Okay, now let's discuss this case. I'm having this carbon connected to oxygen. So can I say the flow of electron will occur towards oxygen? Now how the flow will occur? Double bond, double bond, double bond. So this double bond will shift here. As soon as it shifts here, this carbon will have pi bond, and carbon cannot make pi bonds. So this particular pi bond will shift on oxygen. So one of the canonical which I will get is this one. Now this carbon will have a deficiency of pi electrons. So here I will have positive charge. Here I will have double bond, O negative and H. The double bond and these two pi bonds will remain as it is. So it is one of the canonical. Okay. Now I am having a double bond positive charge conjugated system. Double bond positive charge, and carbocations are also sp2 hybridized. So here also resonance will occur. How the flow will occur? From double bond towards positive charge. Right, students? Okay. So the next canonical is going to be like this. I will have C, O negative, H, and here I will have positive charge. Here the pi bond will come, and here also I will have one pi bond, right? Okay, this is the third canonical. Still I am having double bond positive charge in conjugation, right? Okay, so I can have one more conjugated system. Okay, here this double bond will shift here. The flow of electron occurs from double bond to positive charge, high potential to low potential. So here also I will have the structure like this. Now this carbon will have a deficiency. So here positive charge, O negative, H, and here I will have the double bond, and here also I'm having a double bond. Student, now if I look at this particular molecule, O having negative charge, double bond, positive charge. The flow of electron always occurs from negative to double to positive if it's a conjugated system. And yes, it's a conjugated system, so the flow will occur like this. O negative to this one. As soon as it gets delocalized, carbon will have pi bond, so this double bond will shift here. Right, student? So the next canonical which I will have is this one. C double bond OH. This pi bond has come over here, this pi bond is here, and one pi bond here. So how many canonicals are feasible for this compound? Benzaldehyde, 5. Let's number it. 1, 2, 3, 4, and 5. Right, students? So these are the 5 canonicals of benzaldehyde. Now if I look at this particular compound, can I say the flow of electron is there from ring towards the group? The flow of pi electron is from ring towards the group, right? Why? Because a more electronegative element is connected. Okay, so can I say in this particular case the electron density in the ring is going to decrease, right? We'll discuss about these things just after a few minutes. Right now we are continuing with conjugated system. Okay, so this was our double bond conjugated system. Now let's talk more about this types of conjugation. The first conjugation we have studied is double bond. Once when there was no electronegativity difference, and one case where there is certain electronegativity difference. Okay, so students, now let's discuss the next case of conjugated system, and now we are going to discuss double bond in conjugation with negative charge. So I'm having basically pi sigma negative conjugation. Let's try to understand it. I'm going to take a molecule PH benzene, and it's connected to CH2 negative. Okay, so I'm having a pi bond sigma and connected to carbon containing negative charge. Okay, let's calculate the hybridization of each atom here. If I talk about all the carbon here in the ring, I'm having 6 carbons, and all the carbons are sp2 hybridized, right? sp2 hybridized. Alkenes are always sp2 hybridized. So this carbon is also sp2 hybridized. Now if I talk about this carbon containing negative charge, it's connected to a sp2 hybrid carbon system, right? So can I say this negative charge will be treated as a pi electron component? So what will be the hybridization of this carbon ion? CH2 negative. Again, it is going to be sp2 hybridized itself, right, student? So all the carbon here are sp2 hybridized. Now let's discuss resonance, how the flow of pi electron will occur. Students, we have studied, while studying resonance, the flow always occurs from high potential to low potential. So here the flow will occur from negative charge to double bond. Let's draw it. This one will get delocalized. As soon as it gets delocalized, carbon will have 5 bonds. Carbon cannot form 5 bonds, so this entire pi bond will shift on this carbon atom. So I will have doubly bond CH2 negative like this. It is going to be one of the canonical. Now let's talk about the next canonical. I will have negative charge double bond conjugated system, right? So can I say this negative charge will delocalize here? As soon as it delocalizes, this carbon will have pi bond which it cannot form, so this particular pi bond will shift on this carbon atom, right? So the next canonical is going to be like this, right, student? And double bond, and here double bond. Once again, I am having a negative charge double bond conjugated system. Let's draw this also. This one will shift here. As soon as it shifts here, this pi bond will shift on this particular carbon. So the next conjugated system is CH2 negative double bond, right? Once again, this negative charge is in conjugation with double bond. Once again, I will have resonance and the flow will occur like this. So the last canonical is going to be like this. CH2 negative, right? So if I look at 1 and 5, they are basically symmetrical, right? These two are almost symmetrical. So how many canonicals are feasible here? 5. Let's draw the resonance hybrid of this molecule. First, I am going to draw complete benzene ring. If I look at this compound and if I look at all the canonicals, can I say the pi electron is uniformly distributed on all the 7 carbons, right? So I will have a partial double bond character on all the 7 carbons. Right, student? Okay. So I will have a partial double bond character on all the carbons. Right. This carbon, that is CH2 negative, it's containing a negative charge, and now the negative charge is getting distributed at carbon 1, then at ortho, para, once again at ortho. So can I say negative charge will come over here at both the ortho position as well as para position and at this position. Negative charge is getting distributed at 4 positions. Now if I look at this particular molecule, can I say here the flow of electron is occurring inside the ring or towards the ring? Because of that, can I say the ring is becoming electron rich, or can I say the electron density on the ring is increasing? What will be the impact of that? We are going to discuss after a few minutes. But here the flow of electron is inside the ring. I hope you understood double bond negative charge conjugated system. Now let's discuss few more cases on the types of conjugated system. Double bond in conjugation with positive charge, carbocation, or I can say it like this: pi sigma empty p orbital. Very important case, this one also. Okay, let's discuss it. I'm having a benzene ring, and here I'm taking CH2 positive. Can you tell me the hybridization of each carbon? Or alkenes are always sp2 hybridized, and if I talk about this carbocation, it is also going to be sp2 hybridized. So all the atoms present here are sp2 hybridized. Now the flow of electron occurs from high potential to low potential. So can I say the flow will occur from double bond towards positive charge? Double bond towards positive charge. Okay. So the first canonical which I will have is this one. Right? Here I will have positive charge, double bond, double bond. This is going to be the first canonical of this one. Now, once again I am having a double bond positive charge conjugated system. Okay, let's draw it. The pi bond will shift here. As soon as the pi bond will shift here, this carbon will have a deficiency of pi electron, so it will get a positive charge. Perfect. Next one, positive charge over here. Here I will have one double bond, and here I will have double bond, and here also CH2. Next, double bond positive charge conjugation. So can I say this double bond will move here? Right? As soon as it moves here, this particular carbon will have deficiency of pi electron. So here I will have positive charge. The next canonical is like this. Right, student? Okay. Once again, I am having a double bond positive charge conjugated system. Let's draw it. Double bond positive charge. So this double bond will shift here. As soon as it shifts here, this carbon will have deficiency of pi electron. So here I will have positive charge. Right? So here I am having CH2 positive. Right? So basically I have come back to my structure 1. 1, 2, 3, 4, 5. Once again I am having 5 different canonicals of this phenyl carbocation, right? Okay. Now, or benzylic carbocation, better we'll say it as benzylic carbocation. Okay. Now let's draw the resonating structure, resonance hybrid of this molecule. 6 carbon ring, CH2, positive charge at carbon 1, then positive charge at ortho, para, ortho. So positive charge will get uniformly distributed at CH2 and all the ortho and para positions. So I will have del positive over here, del positive over here, del positive over here, del positive over here. My electron cloud is uniformly distributed on all the 7 carbons. So it's like this. So this is all about a double bond in conjugation with carbocation, double bond positive charge conjugation, or we can say double bond empty p orbital conjugation. Let's discuss one more case. I'm having pH in conjugation with B, H and H, BH2. Whether resonance will occur here or not. The first question is this. All the carbons are sp2 hybridized. What about the hybridization of this boron? Can I say it's also sp2 hybridized? Yes, it's also sp2 hybridized. Steric number is 3. It's having an empty p orbital, right? It can easily accept a pair of electrons. Okay. Now, double bond, and here I am having empty p orbital. So it's an electron deficient species, incomplete octet. Incomplete octet. So the flow of electron will occur towards, from double bond towards boron. Once again, the flow of electron or the flow of pi electron is from ring towards boron, out of the ring, right? Okay, so the first canonical which we will have is this one. Double bond BH, H, now negative. Obviously, now it is having a covalency of 4. Here I will have positive charge, double bond, double bond. Can I say now this double bond is in conjugation with positive charge? We have drawn such structure so many times now. We can easily draw it. Double bond will shift here. I will have BH, H negative. Here double bond, positive charge, double bond. Right, students? Next one, double bond in conjugation with positive charge. This one will shift over here. As soon as it shifts here, this carbon will develop a positive charge. Perfect. Let's draw that structure also. I'm having double bond B, H, H negative. Here I will have positive charge. Here I will have double bond and double bond. Now, negative, double, positive. The flow of electrons from high potential to low potential. So the flow will occur like this. Simple like this. And here I will have my last resonating structure like this. B, H, H and this one. Right, students? It's better to draw the pi bonds in this order. This one, and this one. So these are the 5 different resonating structures or canonicals of this molecule. Once again, it was a conjugated system, pi, sigma, empty p orbital, double bond in conjugation with electron deficient species having sp2 hybridization. There also resonance will occur, and here also the resonance is occurring, or the flow of electron is from flow of electron out of ring. Student, if the flow of electron is out of ring, can I say the electron density in the ring is decreasing once again, right? I hope you understood this type of conjugated system also. Let's discuss one more type of conjugated system. Double bond in conjugation with free radical. Okay, let's draw it. Let's take one example. I'm having pH and CH2 dot. If I talk about this CH2 dot, can I say once again here, the octet is incomplete, 7 electronic species, so will act as electron deficient species and will have a tendency to accept more electron clouds or more pi electron component, right? So here also the flow of electron will occur from ring towards the group, from ring towards the group, right student? Okay, how I will draw here? What I am going to do, I will simply break this double bond, one dot and one dot. Now these two dots will form a double bond and here I will have a dot, right? So can I draw it like this? Double bond CH2 dot and dot. These two dots have formed a double bond and here I will have one dot. Now here I am having a free radical. And this one, the number of pi bond, the number of unpaired electrons should be same, and here also it's same only, right? So it's following the rules for drawing resonating structure. The next one, now can I break this one as dot and dot, and now these two dots will form the double bond, right? So the next canonical which we have is like this, double bond CH2, and here I will have one dot and double bond, right student? Okay, now if I break this double bond once again as dot and dot, homolytic cleavage of this pi bond, so one dot and one dot, these two dots are going to form the double bond and here I will have dot, right? Let's draw that. Like this one, and here I am having dot, and then here I am having CH2. Now what I am going to do, I am going to break this double bond, okay, and the last canonical is going to be like this, CH2 dot, right? Here I will have one pi bond and one pi bond. So these are the 5 canonicals of this particular molecule. 1, 2, 3, 4, 5. This, it's not like that, it's a continuous double bond system. It is just drawn to show you how I have drawn a pi bond here, right? Okay, let's move ahead. Students, while talking about the stability of resonating structure, several times you might have heard linear conjugation, cross conjugation, multiple conjugation. So let's try to understand such type of conjugated system also. The first one, linear conjugation, linear conjugated system. If I talk about this linear conjugated system, it's simply here in such a conjugated system there is unidirectional flow of pi electron components. Unidirectional flow of pi electron component is a linear conjugated system. Like this, I can have a molecule like this. Obviously, every atom, if I talk about this, sp2, 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 all the atoms are sp2 hybridized. And if I look up about the flow of electrons, can I say the flow of electron will occur towards more electronegative element? So it's like this, right? This is how the flow of electron will occur. So the flow of electron is occurring in a uniform direction or single direction. Such a conjugated system is referred as linear conjugated system. Because of linear conjugated system, there is uniform charge distribution, the volume charge density decreases, the potential energy decreases, and stability will increase. Well, let's talk about the next type of conjugated system, and that is cross conjugated system. Okay, cross conjugation. If I explain it in a simple word, here basically you might have studied convergence, all the light rays coming at a single point. So it's here, if I talk about cross conjugation, it's convergence of pi electron. All the pi electron component will come at single point. With the help of one example, let's try to understand it. I'm having CH2 negative, C double bond O, CO, CH3. Okay. If I look at this carbon, hybridization, sp2, oxygen, one of the lone pair will get delocalized because it's a neighbor of sp2 hybrid carbon atom. So this oxygen is also sp2 hybridized. Now, negative charge is in conjugation with double bond, right? Negative charge at higher potential, so the flow will occur from negative charge towards double bond, right? Like this. And lone pair is also at higher potential, so the flow of electrons will occur like this. So can I say all the pi electron components are coming at this carbon itself, right? Basically, it's a sort of cross. They are trying to cross each other, right? Okay. Now, can I say because of that, the volume charge density will increase here? And because of the increase in volume charge density, cross conjugated system will decrease the stability, right? So in general, cross conjugation decreases the stability of a molecule. Why? Because here the volume charge density increases, potential energy increases, and stability decreases. The next one, multiple conjugation. Multiple conjugation. Now let's try to understand this. What do we mean by multiple conjugation? I'm having oxygen, right? And here I'm having a double bond, positive charge, and here also let's assume I'm having a positive charge. Okay, lone pair, lone pair. Okay, now let's have a look at this molecule and let's try to draw the resonance. Okay, lone pair, one of the lone pair will act as pi electron component because it's a neighbor of sp2 hybrid carbon atom. So here the oxygen is sp2 hybridized, sp2, sp2, sp2. Lone pair in conjugation with double bond, lone pair at higher potential will have a tendency to delocalize, and it can get delocalized like this, right? Lone pair is in conjugation with double bond, it will have a tendency to delocalize, and the flow of electron will occur from lone pair towards double bond, lone pair towards double bond, right? So can I say basically from oxygen, once the pi electron is moving in this direction, and here also it's moving in this direction towards positive charge, right? So can I say here basically I'm having a sort of divergence case. From a single source, the pi electron is moving in different direction. Such a system is multiple conjugated system. I have studied three different types of conjugated system. We have studied the first one, linear, cross, and multiple. Cross, convergence, multiple, divergence, right? And linear, uniform distribution or unidirectional flow of pi electron components. I hope you understood it. Let's move ahead. So students, till yet mainly we have learned what do we mean by the term resonance, how do we draw resonance, what are the different types of conjugated system, right? Now let's try to understand the stability of different canonicals, right? So now let's talk about the stability of resonating structures. For this, we are going to discuss few important points. The first point itself, the resonating structure without any charge separation is more stable. In a simple word, we can say a neutral molecule is relatively more stable as compared to a charged one. Let's try to understand it with one example. I'm having CH2 double bond CH, C double bond OH. Okay. If I talk about the hybridization, obviously all the carbon atoms are sp2 hybridized here. So obviously the flow of electrons will occur, and it will occur like this. So now I am having CH2 positive, CH double bond C, O negative H, right? This is going to be the canonical of first one, 1 and 2. Now if someone say you compare the stability of these two canonicals or conjugates, which one is going to be more stable? Obviously the first one. A neutral molecule is relatively more stable as compared to charged one. I hope you understood this particular point. Let us move ahead. Structure with complete octet of each atom is more stable. This is the most dominating criteria. A canonical where the octet is complete, that canonical is relatively more stable. Let's try to understand it. Okay, I'm having a molecule like this, positive charge, double bond, OH, lone pair. Okay, will resonance occur here? For resonance to occur, we should have 3 carbons or 3 atoms which are sp2 hybridized, which can participate in resonance. Planarity is required, right? Okay, so if I look at this particular molecule, sp2 and sp2, neighbor of an atom containing lone pair, and if it's a neighbor of a sp2 hybrid carbon atom, then one of the lone pair will act as a pi electron component, and pi electron component does not participate in hybridization, so this oxygen is going to be sp2 hybridized, right students? Now most important thing, carbocations. If I talk about carbocations, pair of electron deficiency is there, so it's a 6 electronic species. Now if I talk about this one, 8 electrons, and if I talk about even oxygen, 2 bonds and 4, so 2 and 4, 8 electrons. Okay, now let's draw the resonance. Lone pair, double bond, positive charge, they are in conjugation. The flow of electron from lone pair to double bond and double bond to positive charge, so it will be like this, right? So the next canonical which I am going to draw is like this. Double bond, okay, and here I will have OH, oxygen has donated, so it will get a positive charge like this. Now if I compare the stability of these two canonicals, can you tell me which one is more stable? Can I say now octet is complete, 8 electrons. Even if I look at this oxygen, 4, 6 and 1 lone pair. 1 lone pair has delocalized, but 1 lone pair is still there. So 4, 1 sigma 6 and an unshared pair 8. All the atom is having complete octet, right? Octet is complete in every atom. So can I say a resonating structure with complete octet of each atom is relatively more stable? Now if I am asked to compare the stability of these two compounds, definitely second one is going to be more stable as compared to the first one. 2 more stable than 1, and this octet will always dominate. This one will dominate. It's one of the most important criteria while comparing the stability of canonicals or conjugates. Always remember this fact. Okay, let's move ahead. Moving to the next statement which we have on the screen, while comparing the stability of canonicals, the statement says negative charge present on more electronegative element and positive charge on less electronegative elements are more stable. That canonical is more stable where the negative charge is present on more electronegative elements. Student, in a simple word we can say negative charge holding capacity, negative charge holding capacity is directly proportional to electronegativity. Let's try to understand it. If I am having CH2 negative in conjugation with C double bond OH, okay, Here obviously resonance will occur and the flow of electron will occur from negative towards double bond. So the next canonical which we'll have is CH2 doubly bonded C O negative and H. Now let's compare the stability. 1, 2. Negative charge on oxygen, negative charge on carbon. Octet is complete here. The only factor which we need to consider is electronegativity. Oxygen being more electronegative will have better negative charge holding capacity. So this canonical 2 is going to be more stable as compared to 1. Let's take one more case. I'm having OH connected to CH2 positive connected to NH2. Okay. I'm having a molecule like this CH2 and it is containing OH and through one side it's connected to NH2. Obviously, if I look at the hybridization of each atom, oxygen sp2, nitrogen sp2 and carbon is also sp2 hybridized, so resonance will definitely occur. Here octet complete, 8 electrons, 6 electron, 8 electron. Positive charge is on carbon. Now let's do the delocalization. Let's suppose the lone pair delocalizes from nitrogen towards carbon. So one of the canonical which we will get is OH CH2 doubly bonded NH positive, right? Now this is the one canonical. Canonical 1, let's suppose it's structure 1, 2. I can have one more structure, right? Okay. And what will be that canonical? Here the lone pair from oxygen is getting delocalized. So I can have the structure like this. OH doubly bonded CH2 NH2 lone pair. O will have positive charge. So students, I'm having 3 different canonicals, right? Now I'm simply asking you to compare the stability. Please do it. I'm giving you 30 to 40 seconds. Okay, student, if I look at compound 1, is octet complete in every atom? Not at all. So 1 is going to be least stable. The factor of electronegativity, the factor of electropositivity will always come after octet. Octet is the most dominant criteria. So here octet is not complete. So it is going to be relatively less stable as compared to 2 and 3. Now between 2 and 3, positive charge on nitrogen and here positive charge is on oxygen. Positive charge on less electronegative element is relatively more stable. Nitrogen being less electronegative as compared to oxygen. So 2 is going to be more stable. Then I will have 3 and then I will have 1. I hope you understood this particular concept. The factor of electronegativity. But always remember the factor of electronegativity will come after octet. Let's discuss few more cases. Students, that canonical is more stable where I am having a linear conjugation or more number of conjugates. Okay. And if I am asked to compare the stability of, once again, I am having a molecule like this. Okay. And now here. Now, can I say all these 3 pi bonds are in conjugation? Here only 2 pi bonds are conjugation because here the hybridization of this carbon is sp3. So now can you tell me which compound is more stable? They are not the canonicals. They are not the canonicals of each other. Here I am simply talking about the stability of these 2 compounds, compound 1 and compound 2. They are not canonicals, not canonicals. Which one is more stable? Can you tell me? Obviously 1, because here I'm having more number of resonating structure. That compound is more stable, which is having more number of resonating structure, because more is the number of resonating structure, more is the charge distribution, or more is the uniform charge distribution, lesser is the volume charge density, higher is the stability. I hope you understood it. One more case. If I talk about the stability of linear conjugation, cross conjugation and multiple conjugation, student, always remember the stability follows the order. Linear conjugates more stable, then we'll have multiple, and then in the end we will have cross conjugates, right? Because in linear conjugation I'm having more uniform distribution of pi electron components. I hope you understood this one also. Students, a few minutes ago only we had drawn several resonating structures, and in those resonating structures basically a group was connected to a benzene ring, right? A group was there and it was connected to benzene ring. And what this group was doing, either it was donating pi electron component into the ring, or it was withdrawing pi electron component out of the ring. Okay, so what this group is doing here, either it is donating or withdrawing pi electron component from a conjugated system. Now let's move to the definition part. When a group releases or withdraw pi electron component in a conjugated system, it is called as M effect group. So we'll say this group as M effect group, and this electronic effect will be referred as Mesomeric effect. Okay, so what will happen if the group basically donates pi electron? Student, we have studied in inductive effects itself, we are having two types of inductive effect, right? Electron donating groups, electron withdrawing groups. There in case of inductive effect it was sigma electron transmission. In case of mesomeric effect it is pi electron movement, right? So if it is a donating group it will be referred as plus M group, and if it is an electron withdrawing group it will be referred as minus M group. Now let's talk about the impact of plus M group and minus M group on a conjugated system. Okay, let's first of all talk about plus M group. Plus M and this side minus M. I'm having a ring. Okay, and this is connected to a group, and this group is behaving as a plus M. So what it will do? It is the electron donating group. Which type of electron donating group? Pi electron donating group. Now, since it's a pi electron donating group, the flow of electron will occur from group inside towards the ring, and because of that, the electron density in the ring will increase. Right, students? Okay. And if the electron density in the ring increases, the ring is said to be activated. The ring is said to be activated. So if a plus M group is connected to the ring becomes activated. Now let's talk about minus M group. Okay, I'm having a ring, and here a group is connected, and this group behaves as a minus M group. Now what it will do? Here the flow of electron will occur from ring towards the group. Ring will become electron deficient. Electron density will decrease, right? And if the electron density decreases in the ring becomes deactivated. Okay, here the ring is becoming deactivated, here the ring is becoming activated. Now one more thing, if you remember those resonating structures and the hybrid, in case of plus M group, what you will observe, negative charge or del negative charge was there at ortho position, para position and ortho position. So if a plus M group is connected to the ring will basically become electron rich at ortho and para positions. So can I say all the electron deficient species will have a tendency to attack at ortho and para positions. So it is said as OP directed. OP directed. If I talk about this, here if you look at the resonating structures, we had drawn several resonating structures, and what we had observed, a del positive charge was there at ortho and para positions. So will electron deficient species attack at these positions? Not at all. O and P positions are electron deficient sites. So any electron deficient species will not attack here. It will attack at meta position. So minus M group deactivates the ring, and the ring is said to be meta directed. Meta directed. Right, students? In case of minus M group, the ring becomes meta directed. In case of plus M group, the ring becomes OP directed. Ortho and para positions are relatively the electron rich positions. Now the most important point, if we go through all the resonating structures, you will observe either negative charge or positive charge was there at ortho and para itself. It was not there at meta position. So can we say mesomeric effect, M effect, is only applicable at OP positions? It's not applicable at meta positions. I hope you understood what the impact of plus M group and what is the impact of minus M group. Now the most important point, how can we identify whether the group is a plus M group or a minus M group? Let's try to understand. Plus M group, electron releasing group, or we can say it as electron donating group, right? A group which bears either a negative charge or unshared pair of electrons always show plus M effect. How? Let's try to understand. I'm having ring, and here a group is connected, and if this group is having a negative charge, can I say this negative charge is at higher potential with respect to double bond? So the flow of electron will occur from negative towards double bond. Even if this group is containing lone pair, unshared pair of electrons, the movement will occur from lone pair to double bond. Here also the flow of electron will occur towards the ring. The ring will become electron rich, or ring will become activated. So all the group which bears either negative charge or lone pair, such groups are plus M groups. Either negative charge or unshared pair of electron. And if this negative charge is in resonance with the ring, the group behaves as plus M group. Let's look at few examples. O negative. Can I say, will it act as a plus M group? Definitely. Let's see. It's in conjugation with the ring, right? So it will act as a plus M group. Then I can have some of the plus M group. Plus M group. Okay. O negative, then I can have NH2, then I can have NHR, lone pair, then I can have NR2, right, students? Then I can have OH, OR, right? These are certain plus M group. Apart from this, if the ring is directly connected to such groups, NH, C double bond OR, here also lone pair is this nitrogen containing lone pair is directly connected to the ring, will act as a plus M group. I can have O, C double bond OR, oxygen lone pair. This lone pair is in direct conjugation with the ring, will act as a plus M group. Plus M group. So these are the plus M group. Apart from these, even these two also act as a plus M group. Apart from this, even we have phenyl acting as a plus M group. Then we'll have all the halogens, because halogens, if I am having a benzene ring and this ring is containing lone pair, right, it's connected to halogen, halogen will have unshared pair of electron. No doubt halogen being highly electronegative will have less tendency to donate. Still it will act as a weak plus M group, weak plus M group. So all the halogens FCl, Bri, it will also act as a plus M group. Then we'll have NO and NC. So these are the different plus M groups. If these groups are directly connected to the ring, then the ring will become electron rich. It is activated ring. It is ortho para directed ring. Let's move ahead. If I write the relative order of these groups, let's say anionic species will have maximum electron density, so it will have maximum tendency to donate. So the most or the strongest plus M. Then we will have NH2. Then we'll have NHR. Now you can say, why not NHR is having a better plus M as compared to NH2? Students, here the answer is simply on the basis of steric crowding. With increase in the steric crowding, the extent of resonance will decrease. So between NH2 and NR2, NH2 is a better plus M group, right? Then we'll have OH. Then we'll have OR. After this OR, I will have NH, C double bond OR. Then I will have O, C double bond OR. Then I will have phenyl. Then I will have halogens, FCl, Bri. And then I will have NO, NC, right? So these are the relative orders of plus M group. The strongest one is O minus, pH O minus. If I am having, what will happen if I will draw the resonance? Right, the flow of electron will occur like this, and because of that, if I draw the final hybrid structure, let me draw the hybrid ones. What will happen? I will have O partial double bond character on all the 7 atoms, del negative over here, del negative over here, del negative over here, and del negative over here. That's why ortho and para positions are electron rich positions, OP directed one. I hope you understood plus M. Now let's talk about minus M group. Already we have discussed the groups which is having a tendency to withdraw pi electron component from the conjugated system is referred as minus M, right? Electron withdrawing groups. And what this group will do, it will deactivate the ring. It will be a meta directed ring. Talking about the relative order of this minus M group, which all group will behave as a minus M group. These species which are electron deficient, or the group having the pi electron components, and the potential of these pi electron component is less as compared to the double bond, then in that case the flow of electron will occur from double bond towards the group. That group will act as a minus M group. Okay, so I will have nitro, sulfonic, cyano, aldehydes, keto, C double bond OX, anhydrides, ester, acid, and amides. These are the few groups which act as minus M group. Apart from this, we can have more minus M groups. All the electron deficient species, like I can have CH2 positive, right? Here also the flow of electron will occur from ring towards this group, right? So can I say it will act as a minus M? Free radical, electron deficient species, all the electron deficient species will act as a minus M group. Here also the flow of electron will occur from ring towards the group, minus M group. Apart from this, I can have few more cases. I can have BH2, incomplete octet, the species whose octet is not complete, the groups whose octet is not complete, that group will have a tendency to withdraw pi electron component from the ring, will act as a minus m group. Apart from this, I can have PH3 positive. Now, expanded octet. Here phosphorus is having a vacant 3d orbital, so the movement can occur, right? It will also act as a minus m group. So not only these groups, all the electron deficient species which are directly connected to a conjugated system and have a tendency to withdraw pi electron component will act as a minus m group. Okay, what this minus m group is going to do? Let's take one case. I'm having benzaldehyde. We had drawn this resonating structure, so let me directly draw the resonance hybrid. If I draw the resonance hybrid, okay, let me draw resonance hybrid once. Yeah. So I'm having benzaldehyde here, oxygen. This one. Okay. Now, students, the pi electron density will get uniformly distributed everywhere. The flow of electron has occurred from ring towards the group, so it will get delta positive. I will have delta positive over here, delta positive over here, right? And here I will have delta negative, right? So this is the resonating or hybrid of benzaldehyde. It's the real molecule. It is going to be the real molecule. And if I look at this particular molecule, can I say I'm having del positive at ortho as well as at para positions. So all the electron deficient species will attack at meta position. That's why it's a meta directed group. Meta directed group. Now one more question. If I talk about this relative order, here it's simply on the basis of electronegativity, the tendency to pull out the electron cloud, right? NO2 will have very high tendency to withdraw the electron. So it's one of the strongest minus I. If I talk about the acid derivative, or let's talk about aldehyde and ketone first of all. C double bond O H, and here I am having R C double bond O R. We have studied it in inductive effect. Here the del positive because of the 2 plus I is relatively less. So electron deficiency is relatively less. So the tendency to withdraw is relatively less in keto as compared to aldehyde. So aldehyde is a better minus M group, right? That's why aldehyde then keto. If I talk about this acid halides, right? No doubt this X is there and this X will have a tendency to donate pair of electrons, will act as a plus M, but it's a weak plus M. In case of halogen, minus I dominates over plus M, right? But if I talk about the different acid derivative like acyl halide, ester, student remember halogen, in case of halogen, minus I dominates over plus M. So among acid derivative, acyl halide is going to be having maximum minus M effect, right? Why? Because it's connected to halogen, and in case of halogen, minus I is much more dominant as compared to plus M. I hope you understood this mesomeric effect. Students, moving ahead with the applications of resonance, the next thing which we are going to do is the classification of certain organic compounds into aromatic compounds, anti-aromatic compounds, or non-aromatic compounds. First of all, let's talk about the conditions required for a compound to be aromatic. If a compound has to be aromatic, it should fulfill the following criteria. First, it has to be cyclic. Then the most important criteria is planarity. The compound has to be planar. If it is planar, means it has to be a conjugated system, means all the atom has to be sp2 hybridized. It's highly important. Cyclic, planar, conjugated, all the atoms should be sp2 hybridized. And the last but the most important one is it should have 4n plus 2 pi electrons, means it should have either 2 pi, 6 pi, 10 pi, 14 pi, like that. It should follow 4n plus 2 pi electron system. So it should obey Huckel's rule. So for a compound to be aromatic, condition number 1 cyclic, condition number 2 planar, all atoms sp2 hybridized, and condition number 4 it should have 4n plus 2 pi electrons. For a compound to be anti-aromatic, once again it has to be cyclic. For a compound to be anti-aromatic, it has to be cyclic, planar, conjugated, but it should have 4n pi electron system. Means either it can have 4 pi electrons, it can have 8 pi electrons, 12 pi electrons, 16 pi electrons, all like that. So if a compound is cyclic, planar, conjugated, all atoms sp2 hybridized, and if it's obeying 4n plus 2 pi, aromatic. If it's obeying 4n pi, it's anti-aromatic. And rest all the compounds are non-aromatic. Rest all the cyclic compounds, whether it is cyclic or non-cyclic compounds, are aromatic, non-aromatic compounds. For a compound to be non-aromatic, it can be cyclic, acyclic. Obviously planarity won't be there. If it's planar, cyclic and conjugated, then it will be either aromatic or anti-aromatic. So in non-aromatic compound, planarity may or may not be there, and it can contain any number of pi electron system, right? I hope you understood what, and you can easily identify whether a compound is aromatic, anti-aromatic or non-aromatic. Let's try to understand this concept with few examples. The first one, if I look at this particular molecule, sp2, 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 all the carbon atoms are sp2 hybridized, right? Okay, is it a conjugated system? Definitely resonance is there throughout the ring. So cyclic, planar, conjugated, how many pi electrons? 2 pi from here. The positive charge is not counted as pi electron system. So how many pi electrons? 2 pi. So it's obeying 4n plus 2 pi also. It's cyclic, planar, conjugated, and having 2 pi electrons. So the given compound is aromatic. If I look at this one, sp2, sp2, but this one is sp3, cyclic but non-planar. As soon as the atoms in the cycle is sp3 hybridized, the compound becomes non-aromatic. Aromatic. So this is non-aromatic compound. Moving to the third one, cyclic, conjugated system. This negative charge is in resonance with the double bond. So cyclic system, a conjugated system. Now talking about 2 pi from here, and negative charge will give 2 pi from here. So I'm having 4 pi electron system. Cyclic, conjugated, and 4n pi electrons. So the given compound is anti-aromatic. Anti-aromatic. Right? Let's move ahead. Okay. Moving to the next one. Here, sp2, sp2, sp2. But this one is sp3 hybridized. In a cyclic compound, if one of the atom is sp3 hybridized, then the compound becomes non-aromatic. So the given compound is non-aromatic. Non-aromatic. Moving to the next one. sp2, 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 sp2. Alkenes and carbocations are always sp2 hybridized. So all the atoms here are sp2 hybridized. It's cyclic, planar, cyclic, planar, conjugated, and is having 2 pi electrons. So it's obeying 4n plus 2 pi. So the given compound is aromatic. Moving to the next one, sp2, 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 sp2. Cyclic, planar, conjugated, and 2 pi from here and 2 pi from here, 4 pi. So it's obeying 4n pi electron system, the given compound is anti-aromatic. Anti-aromatic. Let's move ahead. Moving to the next question which we have on the screen, and here if I look at this particular compound, here the carbon is sp2, 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 this one sp3 hybridized, right? So the given compound is non-aromatic. If I look at this particular compound, sp2, 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 and negative charge is a neighbor of sp2 hybrid carbon atom, so this negative charge will be treated as pi electron component. Obviously it won't participate in hybridization. This carbon will also be sp2 hybridized, so cyclic planar conjugated, 2 pi from here, 2 pi from here, and 2 pi from here, 6 pi. So the given compound is aromatic. Cyclopentadienyl, aromatic. Moving to the next one, 2 pi, 2 pi from here, 2 pi from here. So it's a cyclic one, cyclic plano conjugated. Every atom's sp2 hybridized, but 4 pi. So the given compound is anti-aromatic. Anti-aromatic. AA stands for anti-aromatic. Moving to the next one, cyclic plano conjugated. It's simple benzene, and benzene is always aromatic in nature, right? Aromatic. Naphthalene, aromatic. 6 pi and 4 pi, 10 pi. It's obeying 4n plus 2 pi. Cyclic planar conjugated, having 10 pi electrons, so it is also aromatic. 2 pi, 2 pi, 2 pi, 6 pi from here, 4 pi from here, 4 pi from here, a total of 14 pi electrons, right? Obeying 4n plus 2 pi, right? Now it's the cyclic planar conjugated and following 4n plus 2 pi, so the given compound is also aromatic. Benzene, naphthalene, anthracene, they all are aromatic in nature. One ring, fused ring, 3 rings are fused to form anthracene here. Okay. Moving to the next one. If I look at the hybridization of this carbon, sp2, rest all are alkene systems, so all the atoms are sp2 hybridized, sp2 hybridized. Second one, it's a cyclic planar conjugated, so the given compound is aromatic, and this particular carbocation is referred as troponium ion, highly stable carbocation. Moving to the next question which we have on the screen, and the question is, I'm having a 8-member cyclic ring, right? And the molecular formula of this compound is C8H8. This compound is referred as COT, cyclooctatetraene. Now, basically, it is nothing but aniline 8. Anilines are having a general formula CnHn. From n equals to 8 to n equals to 12, the compounds are non-aromatic. So C8H8 to C12H12, all the compounds, all the aniline cyclic compounds will be non-aromatic in nature. Non-aromatic in nature. Here also COT, this molecule, although it's a cyclic conjugated planar and having 8 pi electrons, 2 pi, 2 pi, 2 pi, so it should be anti-aromatic, but anilines from 8 to 12 are non-aromatic because of non-planarity. The given compound is having a tub-shaped structure. Tub-shaped structure, and because of the tub-shaped structure, the compound is non-aromatic in nature. Aromatic. I hope you understood this one. Let's move ahead. Moving to the next one. Student, if I look at this particular compound, this compound always exists in Zwitter ionic form. Here, the pi bond will break and oxygen will carry a negative charge, and this one will, the carbon will have a positive charge. Now, if I look at this particular compound, the white marked, can I say it is aromatic in nature? So this cyclic compound will always exist in this ionic form, and we say this ionic form as deuterion plus minus. on the adjacent atom, highly polar and aromatic in nature. This one is aromatic. Why? Cyclic, planar, conjugated and 2pi electron system. So it's a aromatic compound. Let's move to the next one. Here, this particular compound is aromatic and this one is non-aromatic. Whenever any non-aromatic or any compound is connected to aromatic compound, the compound is always aromatic in nature. So this one will also be aromatic one. 10th one is also aromatic. Aromatic connected to a non-aromatic compound. Whenever two cyclic compounds are connected, and if one of them is aromatic, the entire compound has to be aromatic. Okay. This one, highly important one. Basically, I am having two cyclic compounds. Such compounds are azocyclic compounds. Now we need to check whether this compound will be aromatic or not. Okay. Let's break this pi bond. And if I break this pi bond, can I write it like this? Once again in the ionic form. I am doing the heterolytic cleavage. So here I am adding plus, minus, right? Now if I look at this particular compound, 2 pi, 4 pi and 6 pi. So 5-member cyclic ring is having 6 pi electrons. And 3-member cyclic ring is having 2 pi electrons. Both of them are cyclic, planar, conjugated. So this compound will always exist in this form. Once again in deuterionic form. And the compound is aromatic. Right, students? I hope you understood this one. Moving to the next one, the 12th question. How many member cyclic ring? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So it's having a molecular formula C10H10. Right? Cyclic, planar, conjugated and following 4n plus 2 pi. But will it be aromatic? No. Annuleins from C8H8 to C12H12, they are non-aromatic in nature. So this one is non-aromatic. I hope you understood this one also. Let us move ahead. Moving to the next question which we have on the screen. Here I am having a 14-member cyclic ring, C14H14. From 8 to 12, it's always non-aromatic. From 14 member onwards, if I look at this compound, we can say this annuline as weakly aromatic. Cyclic, planar, conjugated, following 4n plus 2 pi, where n equals to here 3. 4 into 3, 12, 12 plus 2, 14. 1, 2, 3, 4, 5, 6, 7. 14 pi electrons. So this particular compound is going to be weakly aromatic. Next one. Moving to the 14th one. Heterocyclic compounds. Apart from carbon, here even nitrogen is also there in the ring. But yes, 2 pi, 4 pi, 6 pi. Now some of the student may say whether this lone pair will participate. No student, it will not participate. Why it won't participate in resonance? Because this lone pair is present in sp2 hybrid orbital. sp2 hybrid orbital. It's not present in the pure p orbital. Right? The lone pair of this nitrogen is present in sp2 hybrid orbital. So it won't participate in resonance. It won't be treated as a pi electron component. So I'm having 6 pi electrons only. And this compound is aromatic. The name of the compound is, or the common name is pyridine. Okay. Next one. 2 pi, 4 pi and one of the lone pair of this oxygen will delocalize and the compound will be aromatic. Right? Once again a heterocyclic compound. If I look at this particular compound also, 2 lone pair, one of the lone pair will participate in resonance. So 2 pi, 4 pi and 6 pi electrons, cyclic, planar, conjugated, aromatic. moving ahead, this one, 2 pi, 4 pi, and one of the lone pair, and now this lone pair will participate. Now you can say here the lone pair of nitrogen is participating in resonance, but here it's not, because here, students, this lone pair is there in pure p orbital, right? Where here the lone pair is present in sp2 hybrid orbital, planarity is not there, so this lone pair is not present in parallel p orbital, won't participate in delocalization, whereas the nitrogen or the lone pair present on this particular nitrogen, it is present in pure p orbital, will delocalize, and the compound is aromatic. Next one, 2 pi, 4 pi. What's the hybridization of oxygen? One of the lone pair will participate in resonance, so sp2. What is the hybridization of this boron? sp2. All the atoms are sp2, so cyclic, planar, conjugated. How many pi electrons? 2 pi, 4 pi, and 6 pi. Yes, even this compound will also be aromatic, right, students? So now I am 100% sure you people have a crystal clear idea about this aromatic compounds, anti-aromatic compounds, and non-aromatic compounds. How to classify a given organic compounds into aromatic, anti-aromatic, and non-aromatic. Right, student? Let's move ahead. Student, moving to the next electronic effect which we have to study. This is the third electronic effect that we are going to study, and this effect is referred as hyperconjugation. Highly important topic for all JEE Mains, JEE Advanced, as well as NEET. Highly important topic. You cannot simply ignore this topic, or you can say one of the most important subtopic after resonance in GOC. Okay, let's study hyperconjugation. Can you define hyperconjugation? It can be defined as the delocalization of CH or CX sigma electron component in the pure p orbital of adjacent atom, right? So students, just like resonance, here also the delocalization will take place, but here we will have the delocalization of sigma electron component, and this sigma electron component will enter to pure p orbital of adjacent atom. So for hyperconjugation to occur, two things are highly important. First, presence of sp2 hybrid carbon or sp hybrid carbon, because in those cases only we will have pure p orbital. And second thing, presence of a highly polar CH or CX bond, right? Let's try to understand it with examples. Student, what I am going to take? I am going to take a molecule CH3 CH2 positive. Okay. If I look at this particular compound, can I say here it is sp2 hybridized, right? If it's sp2 hybridized, can I say here I will have a pure p orbital, and this pure p orbital is vacant, right? Now, this particular carbon will be referred as alpha carbon. Neighboring carbon of a sp2 hybrid carbon or sp hybrid carbon is referred as alpha carbon. Alpha carbon containing hydrogen is referred as alpha hydrogen. This alpha hydrogen is slightly acidic in nature. So what will happen? Because of the polarization, it will have a tendency to get released in the form of H+. And now what will happen? This CH sigma electron will enter to pure p orbital of CH2. and we will have a structure like this. CH, H, it will get released in the form of H plus, and here I will have double bond CH2. Similarly, we can have more number of hyperconjugative structure. Even this hydrogen can also break. This one can also break. Can I say it's similar to resonance? But here one of the bond is completely getting broken. Chemical bond is breaking. And I will have a physical bond here. So it's also referred as no bond resonance. Student, the first thing where this hyperconjugation is applicable. Hyperconjugation is applicable in all such compounds where I'm having alpha hydrogen and a pure orbital. Now in which case do we get pure orbital? In case of carbocation, okay, second alkene, third free radical, and the last one even alkyne also. Now some of you may say, why alkyne? Here also alkynes are sp hybridized. Here also I will have two pure orbital. Instead of having one pure orbital, I will have two pure orbital. So even in alkyne also this hyperconjugation is applicable. But mainly we study the effect of hyperconjugation in these three: carbocation, alkene, and free radical, right? So this hyperconjugation is applicable in carbocation, alkene, and free radical. There are two things which are sufficient for a compound to exhibit hyperconjugation. First, presence of alpha hydrogen. Presence of alpha hydrogen. It's mandatory. If a compound, even its alkene system, even it's a carbocation system, but if it does not have alpha hydrogen, means no hyperconjugation. This hyperconjugation is mainly applicable in polar bonds like CH or CX. And this polar bond CH and CX sigma electrons will move to pure orbital. The effect is hyperconjugation. So, no alpha hydrogen, no hyperconjugation. Second, pure orbital. P orbital. These two things are mandatory for a compound to exhibit hyperconjugation. So students, now let us try to first of all identify or understand what do we mean by alpha carbon, alpha hydrogen, and the most important thing is counting of alpha hydrogen. This is also important because lot of time students gets confused in calculation of alpha hydrogen. Okay, so first we are going to do the calculation of alpha hydrogen. Okay, if I look at this particular compound, alkene, whether hyperconjugation is applicable here or not, the first question is yes, hyperconjugation is applicable here, students. It's sp2, and this one is sp3, right? Can we say this carbon as alpha carbon? And alpha carbon containing hydrogen is referred as alpha hydrogen, 3 alpha hydrogen. Okay, here this is going to be the alpha carbon, and how many hydrogens here? 2 alpha hydrogen. Now sp2, neighbor of sp2 hybrid carbon, so this is alpha carbon. This is also a neighbor of sp2 hybrid carbon, so it is also going to be alpha carbon. 3 alpha hydrogen from here, 3 alpha hydrogen from here, right? So students, we will have total of 6 alpha hydrogen, right? Here we will have a total of 6 alpha hydrogen. Moving to the next one, sp2, neighbor of sp2 but sp3 carbon. This carbon will be referred as alpha carbon, 3 hydrogen, 3 alpha hydrogen. Here alpha carbon, alpha carbon, alpha carbon, these all hydrogens are alpha hydrogen, so a total of 9 alpha hydrogen. If I look at this, whether hyperconjugation is applicable here or not, definitely sp2, so it's having a pure orbital. sp3, sp3, a total of 9 alpha hydrogen. 9 alpha hydrogen. I hope now you might have understood how do we count the number of alpha hydrogen. Let us move ahead. Students, now let's try to understand hyperconjugation in case of alkene. How do we draw hyperconjugative structure in alkene, and what is the impact of hyperconjugation on alkene? Okay, let's take one example. I'm having CH3 CH doubly bonded CH2. Student, if I look at this particular compound, can I say it is sp2 hybrid carbon? This is a neighbor of sp2 hybrid but sp3, neighbor of sp2 hybrid carbon but sp3 hybridized. Such carbons are referred as alpha carbon. And can I say here hydrogen is there? Yes. So is hyperconjugation applicable here? Definitely yes. Now how do we draw it? I'm having CH, H, H, C, H, doubly bond CH2. Student, now can I say since it is alkene, it will the hybridization of this carbon is sp2, so it will have a pure p orbital, right? It will have a pure p orbital, Now what will happen? This hydrogen being somewhat acidic, so what will happen? This sigma electron cloud will, or the sigma bond pair electrons will enter into pure p orbital of this one, of the adjacent carbon, right? As soon as it moves, this particular pi bond will shift to the adjacent atom. So if I draw the hyperconjugative structure, I will have CH, H, this bond will break, and now I will have a double bond here, C, H, CH2 negative. It is one of the hyperconjugative structure. In a similar way, we can have more hyperconjugative structure. And how many hyperconjugative structure we will have? 3. How? Because I am having 3 alpha hydrogen. Each of the alpha hydrogen will break and I will have 1 hyperconjugative structure because of that. So a total of 3 hyperconjugative structure. This is how we draw hyperconjugation in case of alkene. If I talk here, it's simply nothing but sigma or CH sigma delocalization. So can I say here CH sigma electron is in conjugation with pure p orbital. Student, one of the most important thing, if I look at this particular carbon, sp2 hybridized, if I talk in terms of molecular orbital theory, it is having a pi star vacant. Now, what will happen if I talk in terms of molecular orbital theory? This sigma will enter into, or this CH sigma bond pair electrons will enter to pi star, anti-bonding pi orbital, right? So hyperconjugation is also referred as sigma pi star conjugation. Sigma pi star conjugation. Even this particular question was asked in JEE Advanced 2014. Hyperconjugation is also referred as sigma pi star conjugation. Okay, let's move ahead. Let's draw one more structure of hyperconjugation in alkene. And the best example which we can have is PHCH3. Is hyperconjugation applicable here? Let us try to understand. Student, if I look at this particular molecule, can I say sp2? So neighbor of sp2, this is sp3. Can I say this carbon as alpha carbon? Can I say I'm having 3 alpha hydrogen? Yes, so I'm having alpha carbon, alpha hydrogen, sp2 hybrid carbon. Hyperconjugation is applicable. Now, how do we draw hyperconjugative structure? Let's try to draw it. I'm having benzene CH, H and H. What will happen? This CH sigma electron will enter to pure p orbital, right? So I will have the delocalization here, and now because of this delocalization, what will happen? I will have C doubly bond H, H. This H bond will break and it will get physically bonded. Now as soon as it delocalizes, this carbon will have 5 bonds, so it cannot form 5 bonds. So this pi electron will shift on the adjacent atom, so I will have negative charge over here, right? Now can we have resonance here? Definitely yes. So through resonance, this negative charge will delocalize, it will come here. Further from here, this will delocalize, it will come here. So if I draw the resonance hybrid or overall the hybrid structure, can I draw it like this? C, I'm having C, H, H, there won't be any bond. So C, H, 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 all of them will be physically bonded. So H plus dot dot dot, H plus dot dot dot, H plus dot, right? One bond. Now I will have dot. The movement of pi electron throughout the ring, and at ortho and para position, I will have del negative charge. So just like mesomeric effect, even if a alkyl group is connected to a ring, and if this alkyl group is having alpha hydrogen, alkyl group having alpha hydrogen is connected to a ring, then it will activate the ring, and it will be a ring activator and ortho para director. All the incoming electron deficient species will get attached at ortho slash para positions, right students? So this is all about hyperconjugation in alkene. Let's move ahead. Now let us try to understand the hyperconjugation in case of free radicals. In case of free radicals also we have a pure p orbital because the radicals are sp2 hybridized, right? Let's try to understand it. I'm having C, H, 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 C, H, H dot, right student? Here single electronic species. So what will happen? Now once again I will have this carbon is sp2 hybridized, so I'm having a pure p orbital, and in that pure p orbital one of the electron is there. So this one will depart, and I can say basically it will cleave, and I will have H dot, C, H, H, and now I will have double bond CH2. It will get physically bonded. Just like this hydrogen, even these two hydrogens will also get detached from the carbon and will be physically bonded to the carbon. So how many hyperconjugative structure we will have? 3 hyperconjugative structure, right? Okay, let's see few more cases. Hyperconjugation in case of carbocation, one of the most important thing. Okay student, if I look at this particular case, CH2 positive, right? Okay, hybridization is sp2, and can I say here I am having a pure p orbital which is vacant, and here I am having a CH sigma bond pair electrons. So this CH sigma bond pair electron will enter to pure p orbital, or we can say empty p orbital, empty p orbital, and as soon as it enters I will have C, H, H. Now it will be there in the form of H plus, physically bonded to this carbon, and here I will have double bond, right? Even this hydrogen and this hydrogen will also undergo hyperconjugation, and it will also cleave, and can I say it will also be physically bonded. So I will have my final structure like this, right student? Here I will have somewhat partial double bond character, right? and here I will have del positive. Here I am having positive charge, positive charge, positive charge. So this is how we draw hyperconjugation in case of carbocations. I hope you understood it. So student, now it's time to discuss the applications of hyperconjugation. The first thing, student, if we look at the hyperconjugative structure, can I say once again I am having charge distribution. So can I say there is, because of hyperconjugation, the volume charge density will decrease, the potential energy will decrease, and the stability will increase, right? So can I say more is the number of hyperconjugative structure, more is the stability of the compound? Yes. And can I say this number of hyperconjugative structure is simply dependent on number of alpha hydrogen. More is the number of alpha hydrogen, more is the number of alpha H, more is hyperconjugative structure, more is the stability, right? If no other effects are applicable, then while comparing the stability of different alkenes, simply we need to compare, or we need to check the number of alpha hydrogen in each alkene. More is the number of alpha hydrogen, higher will be the stability of alkene. Let's do these questions. Student, if I look at this particular compound, how many alpha carbon? 2 alpha carbon. How many alpha hydrogens? 2 from here, 2 from here, 4 alpha hydrogen. If I look at this one, 2 alpha hydrogen, this one is also alpha carbon, so 2 alpha hydrogen, and this one is also alpha carbon, so a total of 3 alpha hydrogen from here, total of 7 alpha hydrogen, right? 4 alpha hydrogen, 7 alpha hydrogen. If I look at this particular compound, alpha carbon, 2 alpha H from here, 2 alpha H from here. This is also alpha carbon. So from here I will have 3 alpha hydrogen, and from here I will have 3 alpha hydrogen. So a total of 4 and 6, 10 alpha hydrogen. Now if I look at the last compound here, can I say it is a alpha carbon? Alpha carbon, alpha carbon, alpha carbon. These 4 marked carbons are alpha carbon. 1 alpha H from here, 3 alpha H from here, 3 alpha H from here, 1 alpha H from here. So a total of 8 alpha hydrogen. Now, which is going to be the most stable? The one having maximum number of alpha hydrogen. So third one. Then here I am having how many alpha hydrogen? 7, 10, 8, 4. So after third I am going to have fourth, then second, and one will be least stable. 3, 4, 2, 1. More the number of alpha hydrogen, higher is the stability of alkene. Moving to the next one. Alpha carbon, 2 alpha hydrogen, right? 2 alpha hydrogen here, 3 alpha hydrogen, 3 alpha hydrogen. So 6 alpha hydrogen here, perfect. 6 alpha hydrogen here, perfect. And here also 3 alpha, 3 alpha, 6 alpha hydrogen here. Now if the number of alpha hydrogen is same, then how do we compare? Then we look at the geometry. Here if I look at this particular compound, can I say I am having cis configuration? Here I am having a trans configuration. So in between cis and trans, which one is relatively more stable? Students, in general, trans compounds or trans molecules are more stable because of more number of elements of symmetry. So this is more symmetrical, will be more stable. Now, so between 2 and 3, no doubt 3 is more stable. But between 3 and 4, let's check which one is more stable. Student, here also 6 alpha hydrogen, here also 6 alpha hydrogen. Will it show GI? Not at all. Then how do we compare? We can compare by drawing the hyperconjugative structure of this one. Student, if I draw the hyperconjugative structure of this compound, I will draw it like this: CH2 H will remain as it is, it will be physically bonded, and then I will have a double bond C, right? This is CH2 doubly bonded C. Now I will have CH2 negative. So through hyperconjugation, basically pi bond is coming here, and here I am having a negative charge. So if I draw the hyperconjugative structure of this compound, I will have the generation of 1 degree carbanion. If I draw the hyperconjugative structure of this compound, here I will have H, H, H. One of the pi bond will break, so this pi bond, sigma bond will move here, and this pi bond will shift on adjacent atoms, so I will have 2 degree carbanion. Which one is more stable, 1 degree carbanion or 2 degree carbanion? Students, 1 degree carbanion, the carbanion which is less substituted, is relatively more stable. So can I say between this trans alkene and this one, this compound is going to be more stable. So now can we have the relative order? Fourth, maximum, then I will have 3, then I will have 2, then I will have 1. This is the relative order of stability of alkene. While comparing the stability of alkene, if no other electronic effect is applicable, simply check the number of alpha hydrogen. Let's move ahead. Now let's compare the stability of carbocation. Once again, the stability of carbocation, if no other electronic effect is applicable, will simply depend on number of stability, will depend on number of alpha hydrogen. More is the number of alpha hydrogen, higher will be the stability of carbocation. Let's check. 2 alpha, 2 alpha, 4 alpha hydrogen here. Here, 3 alpha from here, 2 alpha from here, 2 alpha from here. So a total of 7 alpha hydrogen. 3 degree carbocation. If I look at this compound, 2 degree, but here I am having 1 alpha and here also 1 alpha. So a total of 2 alpha hydrogen. Now 4, 7, 2. Which is going to be more stable? Obviously, second one. After second, I will have the first one, and after first, I'll have the third one. Student, no doubt here I will have migration of the alkyl group, and finally I will have 3 degree alpha. But if I am given this particular carbocation, then only I am comparing. No doubt this carbocation will undergo rearrangement, and I will have a 3 degree carbocation where I will have more number of alpha hydrogen. But if I am given this carbocation only, if I have to compare the stability of this carbocation, then 2, 1 and 3. I hope you understood it. Next one. Here students, if I look at this compound sp2, sp2, sp2. So is resonance applicable? Yes, resonance is there. Is hyperconjugation also there? Yes. This is alpha carbon, and this alpha carbon is having 2 alpha hydrogen. 2 alpha hydrogen. Resonance along with hyperconjugation. Here, sp2, 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 right? And here I'm having sp3, 1 alpha hydrogen. No doubt here I am having 2 alpha carbon, 2 alpha hydrogen, and here I am having 1 alpha hydrogen. But here the most dominant effect is there, that is hyperconjugation. So student, if hyperconjugation is, resonance is there, if most dominant effect is there, and that effect is resonance. Here more conjugation, more extent of conjugation, more will be the stability of this compound, and I will have 2 greater than 1. In compound 2, once again I am repeating, the extent of resonance is more, the extent of conjugation is more. No doubt the number of alpha hydrogen is less, but resonance is the most dominant effect. If I compare the relative order of electronic effects, resonance, hyperconjugation, inductive effect, right? Okay, let's move ahead. Now moving to the next application of hyperconjugation, sometimes we are asked to compare carbon-carbon bond length in certain organic compounds. Let us try to understand this bond length application with the help of one question. Here we are asked to compare the bond length of these carbons. This carbon CC double bond, this one, and this one. Please do it. I am giving you 30 seconds. Once you are done, please mention in the comment section. Student, if I look at this particular compound, is there any resonance? Not at all. Is there any hyperconjugation? Not at all. So the bond order is perfectly 2. More is the bond order, lesser is the bond length. If I look at this particular compound, is the hyperconjugation there? Yes, 3 alpha hydrogen. Because of hyperconjugation, I will have partial double bond character. Partial double bond, right? Here, 6 alpha hydrogen, right student? Because now if I compare between 2 and 3, where I will have more single bond character in the third one, because the extent of hyperconjugation is more. So if I compare 1 to 3, where CC bond length will be higher in third one. Now if I look at this particular compound, sp2, 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 resonance is applicable, and resonance is the most dominant effect, right? So because of resonance, what will happen? I will have more single bond character here. So I will have maximum bond length observed in fourth, and the relative order will go like this: 4, then I will have third, then I will have 2 and 1. In 1 I will have complete double bond character, so least bond length. I hope you understood this particular question also. Let us move ahead. Now students, moving to the next application of hyperconjugation, and it is going to be the most important application of hyperconjugation. Most of the time you will see questions coming from this particular subtopic, heat of hydrogenation. What do we mean by this term heat of hydrogenation? Student, it can be simply defined as the amount of energy released when 1 mole of an unsaturated compound gets completely saturated with hydrogen. The amount of energy released, amount of heat energy released when 1 mole of an unsaturated compound gets completely saturated with hydrogen. Okay, I'm having CH2 doubly bonded CH2. I'm adding 1 mole of hydrogen here. What I will get? CH3. Now alkene and alkane, which one is more stable? Alkane. So energy will release here, and the amount of energy which is getting released here, that energy is nothing but heat of hydrogenation, delta H. The process is exothermic, so here the delta H will be less than 0. But students, in organic chemistry, the question which you will be asked, you won't be asked calculate the heat of hydrogenation. You will be asked compare heat of hydrogenations of different organic compounds. You will be given a set of organic compounds, and then you need to compare HOH. How do we compare? We are having a simple shortcut, and that is heat of hydrogenation is directly proportional to number of pi bonds. HOH first, is directly proportional to number of pi bonds. And second, if the number of pi bond is same in two compounds, if the degree of unsaturation is same in two given compounds, then in that particular case, HOH is inversely proportional to stability of the compound. Stability. If the number of pi bond is same, HOH inversely proportional to stability. First, we need to check the number of pi bonds or the degree of unsaturation. If the degree of unsaturation is same, then only compare stability. Now let's try to understand this concept with few examples. Compare HOH of the following compound. Okay. 1 double bond, 2 double bond, 2 double bond, and 3 degree of unsaturation. Can you tell me? I'm giving you 30 seconds to answer this question. Please do it. So I hope you have solved this particular question. Now let's try to match your solution and let's try to discuss it. Okay. Student, you can easily say, so here I am having maximum degree of unsaturation. So this compound will have maximum HOH. No, it won't have maximum HOH. No doubt it is having more number of pi bonds and HOH is directly proportional to the number of pi bonds. But this compound is aromatic. And if it's aromatic, can I say it is highly stable? Right? So when I will do hydrogenation of this compound, relatively lesser amount of energy will release. The amount of energy which releases from here is approximately 51 kilocalorie per mole. Here, 2 degree of unsaturation. If I compare these two, the degree of unsaturation is same, but here I am having resonance. Here, no resonance. So can I say here I will have maximum HOH? If the number of pi bond is same, HOH is inversely proportional to stability. Between 2 and 3, 3 is more stable, so 2 will have more HOH. Between 1 and 2, can I say 1 is having less number of pi bonds, HOH directly proportional to the number of pi bonds. So the relative order will go like this. Here approx 29 kilocalorie per mole energy is released. Here 58 kilocalorie per mole. Here approximately 55 and here 51. Right? Why 51 here? It should be 87, but because of resonance, because of aromaticity, the HOH value is relatively less. So the relative order will be like this. I will have 2, 3, 4, 1. Right? Moving to the next question. 1 pi bond, 2 pi bond, 2 pi bond. Obviously here HOH value will be less. Now if I am asked to compare, we can easily say I'm having more number of alpha hydrogen here. More is the number of alpha hydrogen. High is the stability. And if the degree of unsaturation is same, higher is the stability, lesser the HOH. So can I say 3 will have more HOH, then we'll have 2 and then 1. Right, students? Now let's discuss here. Degree of unsaturation 1, 1, 1 pi bond, 1 pi bond, 1 pi bond, 2 pi bond. So can I say this one will have maximum HOH 4. Now I need to compare these three. Here the number of alpha hydrogen, 2 alpha, 1 alpha, 3 alpha hydrogen from here. If I look at this particular compound, I am having 2 alpha from here and 2 alpha from here, 4 alpha hydrogen from here in this compound. And if I look at this compound here, I have 3 alpha from here, 2 alpha from here, and if one more alkyl group is here, then 1 alpha from here. So 3, 1, 4 to 6 alpha. Now if I am asked to compare HOH, has the stability, lesser the HOH. Third one, having more number of alpha hydrogen, more stable, least HOH. So between 1 to 3, can I say 1 will have more HOH, then 2 and then 3. So the order will 4, 1, 2 and 3. This is the relative HOH order in this compound. Let us move ahead. Moving to the next subtopic which we are going to discuss, and it's also the application of hyperconjugation. The topic is heat of combustion. Student, it can be simply defined as the amount of energy released when 1 mole of an organic compound is burnt completely in the presence of oxygen to release CO2 and H2O gas. The amount of energy released or absorbed, generally it's an exothermic process. So the amount of energy released when 1 mole of an organic compound is burnt completely in the presence of oxygen. Okay. In questions, mainly in organic chemistry, you are asked to compare HOC data of certain organic compounds. How do we compare? HOC, heat of combustion, is directly proportional to number of carbon atoms. And if the number of carbon atoms are same, then HOC is inversely proportional to stability of the compound. Now let's compare HOC and let's try to understand this HOC with few examples. Okay, the questions which we have. The first question: 6 carbon, 7 carbon, 8 carbon, and here I am having 7 carbon. Most the number of carbon atom, higher is the HOC. So can I say third one will have maximum HOC and first one will have least HOC value? Now between 2 and 4, here if the number of carbon atom is same, simply compare stability, and in order to compare stability you need to check the number of alpha hydrogen. Okay, 3 alpha, 2 alpha, 2 alpha, so a total of 7 alpha. Here 2 alpha, 2 alpha, so a total of 4 alpha. Between 2 and 4, which one is more stable? 2. So 2 will have less HOC, right? So after 3, I will have 4, then 2, 1. This will be the relative HOC order, directly proportional to the number of carbon atom, inversely proportional to stability, provided the number of carbon atom is same. 3-member ring, 4-member ring, 5-member ring, 6-member ring. With increase in the number of carbon atom, the HOC value increases. Okay, here 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Everywhere I am having 4 carbon atoms. We had done this question, right? 2 alpha. If the number of carbon atom is same, simply we need to compare the stability. If I compare the stability, can I say stability order? We have done this question, right? The stability will be 4 max, then I will have 2, then I will have 3, then I will have 1. So HOC order will be 1 max, then 3, then 2, then 4. Right, students? So I hope you understood this HOC also. So student, this was all about hyperconjugation. Students, till yet mainly we have discussed all the electronic effect, that is inductive effect, resonance and hyperconjugation, and we have studied that resonance is much more dominant, then we will have hyperconjugation, and then we will have inductive effect. Among all these electronic effects, relatively I effect is less dominant, right? Now we are going to discuss the applications of these electronic effects, how these electronic effects affect the stability of certain reaction intermediates, and these reaction intermediates are free radical, carbanion, carbocation, right? So now we are going to discuss the relative stability of these reaction intermediates. First, let's talk about carbocation. Carbocation, it's simply formed by heterolytic cleavage. I'm going to do a heterolytic cleavage of alkyl chain. We are going to get carbocation. 6 electronic species, sp2 hybridized, diamagnetic in nature, right? Now let's talk about the stability. Student, if I talk about the relative stability of carbocation, I will write one order and I simply request you to please mug this order. You need to by heart this relative order. Most of the time, questions will be directly asked on the basis of this order. Okay. So first, the most stable carbocation is the carbocation stabilized by back bonding. CH2OH, right? Or I can have CH2 positive NH2. Can I have resonance here? Delocalization, and because of the delocalization, what will happen? The octet will get complete. So a carbocation stabilized by back bonding is the most stable carbocation, right? Then we will have on number 2, carbocation stabilized by sigma resonance. Okay, sigma resonance is mainly applicable in case of methyl cyclopropyl carbocation. So such type of carbocations are highly stable. Okay, so this carbocation, after the carbocation stabilized by back bonding, on number 2 I will have this one. Then we will have students, then we will have once again carbocation stabilized by sigma resonance. Now 2 ring, right? So I will have this carbocation. Next we are going to have tropylium carbocation, highly stable carbocation. We have studied it, right? In case of aromaticity. This is also a highly stable carbocation because the compound is aromatic. Then we will have this one, once again, carbocation stabilized by sigma resonance, or we say it as dancing resonance. So on 5th, I will have this one. Students, then I will have a very unique thing. 3-degree carbocation. A carbocation stabilized by 9 alpha hydrogen, and this carbocation is more stable than benzylic carbocation, which is stabilized by resonance. So this one you need to remember. Very important. Okay. So on number 7, we are going to have this one, pH, CH2 positive. Students, after that, we will have carbocation stabilized by resonance, that is allylic carbocation. CH2 doubly bonded CH, singly bonded CH2 positive. After that, we will have 2-degree carbocation, that is, right student? Then I will have 1-degree carbocation. Then I will have methyl carbocation, that is CH3 positive. After that, we will have some highly unstable carbocation, and these carbocations can be unstable carbocations, and these carbocations are phenylic carbocation, unstable vinylic carbocation, right? Then we'll have bridgehead carbocations. These carbocations are highly unstable carbocation. Even one more, anti-aromatic carbocation, like this one. All of them, all these 4 are highly unstable carbocation. This relative order of carbocation or relative stability of carbocation, you have to keep it in mind. Highly important. Please go through this order. So students, till yet we have discussed the relative order of stability of carbocation. Now let's discuss the relative order of stability of carbanion. Let's discuss that also. The relative order of stability of carbanion. Okay, I'm having first of all the most stable carbanion. The carbanion stabilized by aromaticity, highly stable, right? Then we will have carbanion stabilized by resonance. Okay, so I will have this one, and if I'm having a minus I or minus M group, then obviously this carbanion will get further stabilized. Then carbanion stabilized by allylic carbanion. I can have this one here also. I can have resonance, right? So let me do one thing. Let me draw this. Right? Allylic carbanion. Then I will have 1 degree, 2 degree, and 3 degree. The least stable carbanion is anti-aromatic carbanion. This is anti-aromatic, right? So it is going to be less stable carbanion. So carbanion stabilized by aromatic, then benzylic resonance, allylic resonance, then 1 degree, 2 degree, 3 degree, and least stable is going to be anti-aromatic. Now let's discuss the relative stability of free radicals. Relative stability of free radical. Free radical. Student, here the free radical stabilized by resonance is the most stable one. So more is the extent of resonance, more is the stability of free radical. Unlike carbocation, right? So here the relative stability, benzylic, allylic, then I will have 3 degree, then 2 degree, then 1 degree, right? So this is the relative order of stability of free radicals, right students? So I hope you understood all these orders, and I am 100% sure you are going to keep it in mind, all these relative orders, right? Let's move ahead. Student, now let's discuss the applications of these electronic effects what we have studied with the help of these questions, and these questions are mainly the PYQs of either JEE Mains, JEE Advanced, and NEET. Let's start our discussion one by one. Okay. If I look at the first compound, here I need to compare the relative stability of carbocation. Let's check the electronic effect operative here. I'm having OMe, and this OMe is present at para position. At para position, mesomeric effect is applicable. Oxygen having lone pair will act as a plus M. Apart from this, OMe also behaves as a minus I. This inductive effect is there at para position, so very weak minus I and strong plus M. Perfect. Here I am having OMe at meta positions. At meta position, mesomeric effect is not applicable, so only minus I effect, right? If I look at this particular compound, OMe, oxygen having lone pair, plus M, right? At the same time, weak minus I. OMe at ortho position also, mesomeric effect is applicable, so I'm having plus M and minus I. Okay, so in compound 3, I'm having 2 strong plus M group and 2 weaker minus I. Obviously plus M is much more stronger as compared to minus I, so it will increase the stability. All the plus groups increases the stability of carbocation, all the minus groups increases the stability of carbanion. Okay, so can I say third more stable? Then I will have 1, and here minus I group, a minus I group or electron withdrawing group will decrease the stability of carbocation. So 3, 1, 2. Let's move to the next question. Student, CS3 here, CD3OH and CT3. Perfect. If I look at this CS3, can I say this CS3 will act as a plus I group? Can I also say it will act as a plus H group? It will stabilize the molecule through hyperconjugation, alpha carbon, alpha hydrogen, so plus H, right? Okay. OH, lone pair, present at, here I am having pi bond, student. You need to keep it in mind. OH having lone pair will act as a plus M group, weak minus I also. Now CD3, alpha carbon containing deuterium, right? So will stabilize this molecule through hyperconjugation, will act as a plus H as well as plus I, right? And here I am having CT3 will act as a plus I group, alpha carbon containing tritium, obviously it will act as plus H. Now can you tell me which one is having better plus H? CH, CD, CT. Student, we have studied more is the mass, lesser is the vibration, more is the stability of bond. So CT bond is more stable as compared to CH bond. And if stability is more, obviously the relative cleavage tendency, the bond breaking tendency will be less. So if I need to talk about the hyperconjugative order, CH will have maximum, then I will have CD, then I will have CT. Why? CH bond is weaker as compared to CD bond. So CH bond can easily be cleaved. Okay. So can I say CH will have a stronger plus H as compared to CT? So if I compare between 1 and 3, can I say 1 is going to be more stable? But in second, I'm having a plus M effect. And plus M is the most dominant effect. So the relative order is 2, 1 and 3. I hope you understood these two questions. Let's move ahead. Highly important. Okay. So students, basically through these questions, we will even touch those topics which we could not cover in the theory part. So I sincerely request you to do all the questions and listen carefully whenever I am giving the explanation of these questions, because these questions are really important for all your upcoming exams. Okay. Now, I need to compare the stability of these carbocations. Let's compare the electronic effect operative here. Nitro group, strong minus I, strong minus M. OH, minus I plus M. OH present at ortho position plus M, weaker minus I. Now, here minus I and minus M will decrease the stability of carbocation, right? Plus M will increase the stability of carbocation. Perfect. So can I say 3 and 4 is going to be more stable as compared to 1 and 2? Because here I am having plus M group, right? Now between 3 and 4, which one is more stable? Can you tell me? Here minus I is present at para. Here minus I is present at ortho. Minus I present at ortho. I is a distance dependent effect. Here minus I is much more dominant as compared to this one, right? Mesomeric effect is same. Inductive effect dominates in fourth one. So fourth is going to be relatively less stable as compared to third one. 3 more stable than 4. Second is going to be least stable, right? All the electron withdrawing groups decreases the stability of carbocation. So 3, 4, then I will have 1, then I will have 2. Moving ahead, moving to the next question which we have, this one. Now I need to compare the stability of carbanion. A carbanion gets stabilized by minus I and minus M group, right? Okay. No, nothing. Only this carbanion will get stabilized by resonance. Here I'm having a cyano group, acts as minus M and minus I, and this minus M group will increase the stability of carbanion. Perfect. Cyano group present at meta position, I will have only minus I effect operative here. NO2 present at meta position, only minus I. Now between cyano and nitro, which one is stronger? Obviously nitro. Now here I am having OH present at ortho position plus M minus I. OH present at para position plus M minus I. Now, can you compare the stability of all these 6 compounds? It's very simple. First check all the electron withdrawing group. The electron withdrawing group will increase the stability. Okay, so I'm having electron withdrawing group minus M applicable here. So can I say second is going to be the most stable, because minus M is the most dominant effect which will increase the stability of carbanion to more stable. Then I will have reference here cyano and here nitro. No mesomeric effect but inductive effect, and minus I of NO2 is stronger than that of CN. So can I say 1, 2, 3, 4? 4 will be more, and then I will have third one, right student? Now in these two compounds, plus M effect is there. Plus M decreases the stability of carbanion, right? So after this I will have first. Now I need to compare the stability of 5 and 6. Plus M minus I at ortho is more dominant than minus I at para. So can I say this minus I will increase the stability of carbanion, right? So between 5 and 6, can I say 5 is going to be relatively more stable as compared to 6. So I will have 2, 4, 3, 1, then 5, and then 6. I hope you understood this particular question. Please copy it. Students, moving to the next question which we have on the screen. Here I am having carbocation. And if I look at this carbocation is stabilized by sigma resonance. A carbocation stabilized by sigma resonance is a highly stable carbocation. Methyl cyclopropyl carbocation stabilized by sigma resonance, or we say dancing resonance, right? Here now 4-member cyclic ring carbocation, 5-member cyclic ring carbocation, 6-member cyclic ring carbocation. Can I say here angle strain is more? As the number of carbon chain increases, the strain will get somewhat reduced, right? So stability will be more. So if I compare 2, 3, 4, 4 will be more stable, then I will have 3, then I will have 2. But if I compare overall, a carbocation stabilized by dancing resonance is the most stable carbocation. So the relative order 1, 4, 3, 2. Now let's move ahead. Moving to the next question, students, which we have on the screen, and the question is, I'm having a carbocation, and this carbocation here I'm having 6 state, but this carbocation is stabilized by back bonding, and because of back bonding octet will get completed, right? And we have studied a carbocation stabilized by back bonding is a highly or the most stable carbocation, right? No doubt here the carbocation is stabilized by resonance, but the carbocation stabilized by back bonding is the most stable one. So this one, right student? Moving to the next question. Here I'm having a ring, and this ring is fused with one more ring, and it's in here I'm having a carbocation, and I need to compare the stability of carbocation. Can we say here I will have resonance from here to here? So can I say here in this particular case I will have more number of conjugates. More is the number of conjugates, higher is the stability of carbocation. So here the conjugates will be from here to here, right? So students, obviously this carbocation is going to be more stable as compared to second. Why? Here I'm having more number of resonating structures. Because more and more atoms are sp2 hybridized, so I will have a linear conjugation and extended conjugation as compared to this one. So one is more stable than 2. Let's move ahead. Yeah, even this particular example is also highly important. I suggest you to do on your own and then match the solution. Okay. Student, if I look at this particular compound, oxygen having lone pair, sp2 will get delocalized and the resonance will occur like this. So here I'm having back bonding plus extended resonance. Back bonding plus linear conjugation, right? Linear conjugation. If I look at this particular case, here also the carbocation will get stabilized by back bonding, and the carbocation stabilized by back bonding is more stable. But here also this carbocation is stabilized by back bonding, because as soon as this pi bond shift here, I will have carbocation here and will get stabilized by back bonding. Now if I need to compare between 1 and 2, here apart from back bonding, I am having an extended conjugation, right? Okay. Now if I look at this one, will this carbocation get stabilized by back bonding? Not at all. Only one effect is applicable, that is hyperconjugation. So 1 alpha, 2 alpha, total of 3 alpha hydrogen. Here back bonding plus extended conjugation, back bonding, hyperconjugation. Back bonding will be the most dominant. So back bonding plus extended, then we'll have back bonding and then this one. The relative order 1, 2, 3. I hope you understood this. Moving to the next question which we have on the screen. And this question is also really important. Why? This NR3 acts as a minus I group and a strong minus I group, right? If I look at this PR3 positive, can I say in case of phosphorus, it belongs to third period elements, and or we can say it is there in the third period, and can I say we will have vacant 3d orbital, so it can have extended octet, and because of that it can act as a minus M group, right? NR3 will act only as a minus I group, but PR3 positive, because of presence of 3d, it can even act as a minus M group, and because of that a minus group will increase the stability. Why PR3 positive will act as a minus M group? Because it is having a vacant or empty 3d orbital, right? Here we can have expanded octet, we can have 10 electronic species, right? But NR3 cannot form. Second period element does not have expanded octet because of the absence of empty d orbital. So obviously minus M, a carbanion stabilized by minus M will be more stable as compared to the carbanion stabilized by inductive effect. Next one, highly important, CF3 and CCl3 negative. Students, in case of CCl3 negative, chlorine is having a vacant 3d orbital. So this negative charge can get delocalized in the vacant 3d orbital of chlorine. So I will have p pi d pi back bonding, right? 2p 3d back bonding. Or we can have d orbital resonance. We say this as d orbital resonance, right? The negative charge present on carbon gets delocalized to the vacant 3d orbital of chlorine. Because of that, CCl3 negative will be more stable as compared to CF3 negative. Will d orbital resonance occur in CF3 negative? The answer is no. Why? It does not have empty d orbital. So this one is more stable, right? Let's move ahead. Moving to the next question which we have on the screen, and student, if you look at this particular question, it's all about the application of reverse hyperconjugation. You will say, sir, we had not studied reverse hyperconjugation. I will say, don't worry. Simply, we have studied hyperconjugation, and we have studied hyperconjugation is mainly applicable to the polar bonds like CH and CX. So if it is a CH bond, I will have hyperconjugation. If it is a CX bond, I will have reverse hyperconjugation. Will all CX bond undergo reverse hyperconjugation? Not at all. Only CCl. Among halogen, only chlorine will do this reverse hyperconjugation. Now, one more thing. Okay, so hyperconjugation activates the ring. Here, there is a movement of sigma electron into the ring. In reverse hyperconjugation, the movement of pi electron occurs out of the ring. So it will deactivate the ring, right? Okay. Second thing, you can tell me, sir, you have told hyperconjugation is mainly applicable in case of carbocation, carbon free radical, alkene and alkyne, right? You told hyperconjugation is not applicable in case of carbanion because carbanions are sp3 hybridized. That's why it's not applicable. If carbanion is in conjugation, means if it is sp2 hybridized, can I say here I will have a pure p orbital? That's why in definition I had given CH in conjugation with pure p orbital, I will have hyperconjugation. I didn't say CH in conjugation with alkene, CH in conjugation with carbocation. CH in conjugation with sp2 hybrid carbon, I will have hyperconjugation. I hope you understood it. Now let's look at the examples. I'm having CCl3, strong minus I, but it's there at para position. At para position, from carbon number 4, the intensity or the field intensity of inductive effect is very less. So I will have a weaker minus I. At the same time, I will have a minus H applicable here, right? Because CCl3 will do reverse hyperconjugation. Perfect. Here I am having CF3. Will it do reverse hyperconjugation? Not at all. Only CCl bond will do reverse hyperconjugation. So only minus I. And if I look at this one, minus H, like hyperconjugation, this reverse hyperconjugation is also applicable at ortho and para. So minus H, minus I. If I compare 1 and 3, minus I at ortho is more dominant. So I will have the relative order like this: 3, then 1, and then 2. 3, 1, 2. I hope you understood it. Let's move to the next question. I'm having an electron deficient species free radical, and here I need to compare the stability of these free radicals. Okay. This free radical is getting stabilized by resonance with the ring. Perfect. Apart from resonance, I'm having a plus H effect applicable here, and plus I of alkyl is also applicable here. So, right? Plus H as well as plus I. Here plus H, plus I. Here also plus H, plus I. All the electron deficient species get stabilized by electron donating group. Now between CH3, CD3 and CT3, already have discussed hyperconjugative effect of CH bond is more as compared to CD, and CD is more as compared to CT. So here the plus H will be more. So can I say 2, then I will have 3, then I will have 4, and 1 is the reference. This will be the relative order of stability of these free radicals. Students, I hope you understood all these questions, right? Now we'll move to the next application, or we can say the most important application of electronic effect. And now we are going to discuss highly important concept, that is the concept of acidic strength and basic strength. Students, let's start our discussion with this concepts of acids and base. First, we are going to talk about different types of acid. The first acid is areneous acid. This species having tendency to release H plus in aqueous solution. Then I am having Bronsted acids. They are nothing but the species which are proton donors. Proton donors are basically Bronsted acids. Proton H plus donor. The third one, Lewis acid, electron pair acceptor. Electron pair acceptors. They are having a tendency to accept a pair of electrons. So they are the electron deficient species. I hope you understood all these three different points: areneous acids, Bronsted acids, and Lewis acids. But here, most of the time we'll be talking about Arrhenius acids itself. Student, here most of the question what you will see, in the questions you will see, they ask you to compare the relative acidic strength of organic compounds. Okay. Students, generally organic acids are the weak acids. If it is a weak acids, for them we can define Ka, right? So we can measure the relative acidic strength with the help of Ka. Right? Once we know the Ka value of certain organic acids, we can easily compare. The one having higher Ka value will have higher tendency to release H+. Larger the Ka, higher will be the acidic strength. Smaller the Ka, smaller will be the acidic strength. But once again, all the time you cannot remember the Ka value of each and every organic compound. So there will be certain formula, certain tricks through which we can compare the relative acidic strength. Let's first of all talk about scale of measuring acidic strength. Scale of measurement of acidic strength. Students, let us assume I'm having a weak organic acid Ha. This weak organic acid Ha will dissociate as H plus A minus. Can I define dissociation constant Ka for this? Will be equals to H plus concentration into A minus concentration upon Ha. Right? So can I say higher the value of H plus, higher is going to be the Ka, and H plus value is all about acidic strength, right? So can I say those acids which have higher Ka value will have higher acidic strength, right? Now, sometimes they simply say you compare the Ka value of different acids. Simply you need to compare the acidic strength. The one which is stronger acid, for that particular acid the Ka value will be higher. Sometimes they give in terms of pK. They will give you certain organic compounds and then they say you to compare pK of these acids. Students, if I talk about pK is nothing but minus log of Ka, right? So acidic strength is inversely proportional to pK. Smaller the pKa, greater is the acidic strength. Smaller the pKa, greater is the acidic strength. Students, it was all about measuring the acidic strength with the help of Ka value. But all the time we cannot go to lab and measure the Ka value and all these things, right? These are thermodynamic parameter. We need to know a lot of things, then only we can measure Ka value and compare the acidic strength. And all the time we cannot do it. So we have a certain tricks and formula through which we can compare the relative acidic strength. How do we compare? Let's see. I'm having a weak acid Ha. Step 1. Remove the most acidic hydrogen of the compound. Most acidic hydrogen of compound. Remove the most acidic hydrogen of the compound. Okay. How will you come to know that which hydrogen is more acidic? The hydrogen which is connected to more electronegative elements, right? Hydrogen connected to fluorine, oxygen, they are relatively acidic in nature. So you need to simply remove that hydrogen which is connected to a highly electronegative elements, right? Okay. Once you remove it, suppose if you remove hydrogen from here, what you will get? A minus. Now student, can I say this Ha and A minus, they are nothing but conjugate acid base pairs. If this one is an acid, then it will be your conjugate base. Conjugate base, right? In conjugate acid base pairs, if you remove H plus from the acids, you are going to get an anion, and that particular anion will be referred as conjugate base. One example, HCl. HCl is an acid. If I remove H plus from here, what I am going to get? Cl minus. So this Cl minus is a conjugate base of the acid HCl. I'm having H2SO4. And now someone say SO4 2 minus is a conjugate base. Is it a conjugate base? Not at all. Conjugate acid base pair differs by 1 H plus. So the conjugate base for this one is going to be HSO4 minus, right? So what I have done in step 1, I have removed the most acidic hydrogen. I have formed the conjugate base. Step 2, check the stability of conjugate base A minus, right? Check simply the stability of the conjugate base A minus. And step 3, higher the stability of A minus, better is the acidic strength. Step 1, remove the most acidic hydrogen, form the conjugate, check the stability of conjugate. Higher is the stability of conjugate, better is the acidic strength. Students, now it's time to understand this concept of acids with help of certain examples. So from here onwards, we are going to take different compounds and we will compare the relative acidic strength of those compounds. Student, now let's compare between ammonia and alkyne. Okay. Now I need to compare NH3 and HC triple bond CH. If you are asked to compare the acidic strength of these compounds, how will you compare? You will simply say, sir, here hydrogen is connected to a better electronegative element, so ammonia has to be a good acid. But student, here the percentage character is 50%. In case of terminal alkyne, the acidic strength is really good, and mainly in case of acetylene. Here, if I talk about this compound, the percent S character is 50% S character, and because of that 50% S character, electronegativity of carbon is really good, and because of that, even terminal alkyne is a better acid as compared to ammonia. Okay, now if I have to compare, so I have compared CC, I have compared CN. Now it's time to compare CNO. Okay, so I'm having H2O, right? Then I'm having NH3, then I'm having ROH, okay, and then I'm having HC triple bond CH. Okay, how do we compare? Compare the Ka value. It's 1, 2, 3 and 4. Students, always keep it in mind, the acetylene will be a better acid as compared to ammonia. But is it a better acid as compared to water? The answer is no. Water is always a better acid. Now, okay, so the relative order, ammonia is going to be at the bottom. Then I will have term this alkyne. Now between water and alcohol, how do we compare? We have a simple trick, right? Water and alcohol, ROH. Remove the most acidic hydrogen, OH minus. Remove the most acidic hydrogen, form RO minus. Compare the electronic effects. Here I am having alkyl group. Alkyl acts as a plus I group, and because of that alkyl group, the electron density will increase, the stability will decrease, right? So can I say OH minus is more stable? And if OH minus is more stable, can I say H2O will be a better acid as compared to ROH? But is it applicable for all the aliphatic alcohols? Student, not at all. There is one aliphatic alcohol which is a stronger acid as compared to water, and that is methanol. So let me write except methanol, CH3OH. So if I compare the relative acidic strength, I will have methanol, CH3OH, then I will have water, then I will have aliphatic alcohol, then I will have, students, terminal alkyne, then we will have ammonia, and the rest of the hydrocarbon like alkene and alkyne, right? So I hope you will remember this Ka order. Now you may say, so here also alkyl is having a plus I, but this plus I of methyl is not that dominant as compared to ethyl and other alkyl group. One more thing, if I look in terms of, if I draw the structure of methanol, because of this bulkiness, CH3, the bond angle theta value will increase, right? And because of the increase in bond angle, the percent S character will increase. And because of that increase in the percent S character, the acidic strength of methanol will be higher. I hope you understood it, right? Let's move ahead. Students, since we were talking about alcohols or acidic strength of oxygen containing compounds, already we have done the discussion of aliphatic alcohols. Now it's time to talk about aromatic alcohols. Between aliphatic and aromatic alcohol, which one is a better acid? Let's first of all compare that. I am having cyclohexanol and phenol. Which one is a better acid? Simply remove the most acidic hydrogen. I am having O minus, and here I am having PHO minus. Can I say this PHO minus is resonance stabilized? So this one is more stable. Phenoxide ion is more stable as compared to this one. The conjugate which is more stable, the parent acid of that conjugate is going to be a better acid. So phenol is a better acid as compared to cyclohexanol or any other aliphatic alcohol, because aromatic alcohols are resonance stabilized, right? Now let's talk about the acidic strengths of aromatic alcohol. Students, I'm given three different aromatic alcohols: phenol, phenol, phenol. At ortho position, one electron withdrawing group is attached here. No group, one electron donating group is attached here. Can I say, because of the presence of this electron withdrawing group, the acidic strength of phenol will increase. Why? Because I will remove the most acidic hydrogen one. Now this conjugate will get stabilized by this electron withdrawing group. Higher the stability of conjugate, better is the acid strength, right? So whenever any electron withdrawing group is attached to an acid, the acidic strength increases. Whenever an electron donating group is attached, the acidic strength decreases. So first, I will have higher value of acidic strength for this ortho substituted phenol. Then I will have simple phenol, and here at ortho position I am having an electron donating group. This electron donating group will destabilize the conjugate, and if conjugate is not stable, acidic strength won't be that good. I hope you understood it. Please compete. Students, here we need to compare the acidic strength of these three compounds. Let's compare. Highly important questions. Every year in one of the NEET paper you will find, NEET paper or NTA JEE mains paper, you will find this question. Definitely it is going to come. Every year it will come. Okay, let's try to solve it. Here students, if I talk about this nitro group, can I say it's a minus I and minus M group, and strong minus I, strong minus M. Here also I'm having a strong minus I and strong minus M. At ortho and para position, mesomeric effect is applicable. NO2 is a minus M group, so strong minus I, strong minus I, strong minus M, strong minus M. Here at meta position, only inductive effect is operative, so here only minus I. We know that a strong electron withdrawing group increases the acidic strength. So obviously here I am having a strong mesomeric effect. Obviously these two compounds are going to be a better acid as compared to the meta substituted or meta nitrophenol, right? Now let's compare the acidic strength of these two. You can say, sir, mesomeric effect is same here. Same here. Here inductive effect is at para position, and here the inductive effect is at ortho position. Inductive effect at ortho will be a somewhat dominant effect. So ortho substituted nitrophenol should be a better acid. I will say no. No doubt I am having a strong minus I operative here. But student, here one more effect is operative, and that effect is intramolecular hydrogen bonding. Let's try to draw that. Ortho nitrophenol. OH N double bond O. Now can I say I'm having this hydrogen connected to a highly electronegative element, and here I'm having oxygen. So between this hydrogen and oxygen, can I say I will have a physical bond, and this physical bond is intramolecular H bond. Because of that, now can I say this hydrogen is somewhat physically bonded to this oxygen, so the releasing tendency of this H plus will get reduced. Releasing tendency of H plus will be less, and because of that acidic strength will decrease somewhat. So can I say this orthonitrophenol will be somewhat weaker as compared to paranitrophenol. No doubt here minus I and minus M is operative, and minus I at ortho is more dominant, but because of intramolecular hydrogen bonding, acidic strength is somewhat less. So the Ka value will follow this order. Right students? I hope you understood it. Let's move ahead. Now I am having ortho substituted phenol, para substituted phenol, meta substituted phenol. Students, we have already studied that this CCl3 shows minus H and minus I effect. So at ortho position, minus H is also applicable, minus H, minus I. CF3 will show only minus I. CCl3 will show minus I minus H. And here CCl3 at meta position will show minus H only. This hyperconjugative effect, like mesomeric effect, is applicable only at ortho and para position. Now we can easily tell strong minus H, strong minus I at ortho will dominate, right? So I will remove the acidic hydrogen, I will form the conjugate, remove the acidic hydrogen, form the conjugate, remove the acidic hydrogen, remove the acidic hydrogen, and check, compare the stability. This minus H and minus I will stabilize the anion. So 1 maximum, then I will have third one, right? Now between 2 and 4, here inductive effect is at meta, here strong inductive effect is there at ortho position. This one is going to dominate. So 1, 3, 2, 4. This is going to be the Ka acidic strength order. Right students? I hope you understood this one also. Students, moving to the next question which we have on the screen, and the question says, I'm having phenol, and at ortho position I'm having OCH3 group substituted, right? Here at meta position this OCH3 is substituted, and here at para position this OCH3 is substituted. Now let's check the electronic effect operative here. Here I'm having plus M, minus I, only minus I, plus M, and very weak minus I, right? OR, relatively very weak minus I, and that too at para position. So this minus I effect will also be somewhat negligible. Okay. Now we need to compare the acidic strength. Obviously, electron donating group like plus M, which is a very strong electron donating group, will destabilize the anion, so acidic strength will be less. 1 and 3 will have relatively less acidic strength as compared to the meta substituted phenol, right? So if I compare the Ka value to maximum, now we need to compare between first and third. Student, here what you will find in case of orthonitrophenol, that para 1 was dominating, because in case of orthonitrophenol I was having hydrogen bonding. Here also we can have hydrogen bonding, right? Here also I can have this hydrogen bonding. But if I compare the relative acidic strength, and if we go through the Ka value, the Ka value of this ortho substituted phenol is higher as compared to the para 1, and the basic reason is here the inductive effect is really very weak. So almost negligible inductive effects. No doubt here intramolecular hydrogen bonding is there. Because of that, somewhat acidic strength will decrease. Still, this ortho substituted will dominate over para 1. I hope you understood it. So you can remember it as exception 1 somewhat. Okay, let's move ahead. Moving to the next question which we have on the screen, and student, here we need to compare the relative acidic strength of halophenols. Okay, I'm having ortho substituted phenol everywhere. Here it is fluorine, chlorine, bromine and iodine. In case of halogen, minus I of halogen is greater than the plus M of X, right? So what this minus I will do? This minus I will increase the acidic strength. Now let's first of all compare this plus M tendency. Plus M of fluorine is relatively better as compared to chlorine, bromine and iodine. Why? Because here I'm having a 2p 2p overlap. Here 2p 3p overlap. 2p 4p overlap. 2p 5p overlap. So this iodine will have the weakest plus M, right? Why? Because 2p 5p overlap will not be that effective. Here the lone pair is present in 5p orbital, and if it has to delocalize, the delocalization will occur from 5p to 2p, which is not that effective. So ideally it should be a better acid, but no, only the plus M is not the dominant criteria here. Here minus I dominates, and you will say minus I of fluorine is better, plus M of fluorine is also better. They are contradicting with each other. Student, the overall order goes like this. First I will have OH substituted with Cl, then I will have OH substituted with Br, then I will have OH substituted with I, and at last we will have OH substituted with fluorine. The first region, fluorine, is having a better plus M. Second region, and the highly important region, once again, intramolecular H bonding, IMHB, and because of that even the acidic strength will be somewhat lesser. I hope you understood this acidic strength of halophenols. Let's move ahead. Students, we have compared the acidic strength up to alcohols. Now let's move towards acid. The weak carboxylic acid, although among the organic acid, it is much more stronger as compared to alcohols, hydrocarbons, amines, all these things. It's a much more stronger acid. Okay, so if I write the relative acidic strength of, first of all, let's talk about monocarboxylic acid. Acidic strength of carboxylic acid. Acidic strength of carboxylic acid. I will have the order. First of all, I will have formic acid, HCOOH. Then I will have benzoic acid, and then I will have other aliphatic acids. Now you will say, sir, here benzoic acid is resonance stabilized, so why not? It's a better acid as compared to formic acid. Student, here we say somewhat a weak plus M of this phenyl is operative. Weak plus M of phenyl. So now you will say, sir, and here I'm having plus I. Now you can say the plus M is dominant over plus I. So now this benzoic acid should be weaker acid as compared to other aliphatic acids also. Student, I will say no. No doubt it is a plus M effect, but this effect is almost negligible. At the same time, this phenyl is having a weaker minus I also, right? No doubt it's a plus M, but this plus M is really very weak. Negligible plus M effect, right? So because of that, formic acid, then we'll have benzoic acid, and then we'll have other carboxylic acid. And all these acids will dominate over phenol, and this phenol will dominate over methanol. Methanol will dominate over water. Water will dominate over all other aliphatic alcohols, right? So this is going to be the relative acidic strength, right? Let's move ahead. Student, now let's talk about the acidic strength of dicarboxylic acid. In dicarboxylic acid, we are going to have two acidic protons. So obviously, I will have two dissociation constant Ka1 as well as Ka2. Let's first of all talk about a few dicarboxylic acids. I will have OMS, O M S G A P. Although we don't need to remember each and every one, and we'll compare a few. O stands for oxalic acid. Oxalic acid. The formula is going to be COOH, COOH, 0 CH2 group. Then malonic acid. Malonic acid. Here I will have one CH2 group between two acids. So it will be CH2, COOH, COOH. This CH2 group will act as an alkyl group. So obviously, as I move from O to M, M to S, I will have more and more CH2 getting added. And because of that, the acidic strength will decrease. So if someone asks you which one is a better acid, oxalic acid or malonic acid? Oxalic acid, right? Then we'll have succinic acid. Succinic acid, right? The formula will go like this: CH2, CH2, COOH, COOH. Then glutaric acid, and like that. Glutaric acid. Here I will have 3 CH2 group present. CH2, CH2, CH2. And here I will have COOH. Here I will have COOH. Student, now if I ask to compare the acidic strength of these four compounds, obviously the first one, the most acidic, is going to be oxalic, then malonic, succinic, glutaric, adipic, and like that. I hope you understood it. Let's move that ahead. Student, now this particular question you will find everywhere in almost all the books which you are solving, right? Even you will find this question in several pre-YQs, whether it has been asked in JEE mains, even in NEET also. So I sincerely suggest you to do this question on your own, and do mention in the comment box once you have solved this particular question. Let's do it. I'm having malic acid and fumaric acid. First, and both of them are dicarboxylic acid. I need to compare first Ka1 value, the first dissociation constant, and then I need to compare the second dissociation constant. Okay, let's first of all remove one acidic hydrogen. I'm having C doubly bonded C, COOH, COO minus H, H, right? Okay, and here I'm having C double bond O, COOH, C double bond O minus H and H. Student, now if I look at this particular compound, I'm talking about Ka1. I have removed the first acidic hydrogen in both the compounds, right? Malic acid as well as fumaric acid. Now if I compare their relative stability, can I say here I may have this hydrogen bonding, and because of hydrogen bonding the stability of this anion will be more as compared to this one, right? So and if this anion is more, so can I say Ka1 of malic acid is greater than that of Ka1 of fumaric acid, right? Now let's talk about Ka2. Now I am going to remove the second most acidic hydrogen. Okay, I'm removing it. Now I will have COO minus, COO minus H and H, and here I will have COO minus, COO minus H and H. Will I have hydrogen bonding here? No, there is no acidic hydrogen. For hydrogen bonding to occur, there has to be acidic hydrogen. There is no acidic hydrogen. Now, can I say two anions on the same side? It will undergo, or it will face inter-electronic repulsion. Because of that, the stability of the compound will decrease. So if I need to compare the stability of these two compounds, can I say this one is going to be more stable, because here the anionic groups are exactly at opposite side. So here I will have minimum inter-electronic repulsion. This one is more stable, and if the conjugate is more stable, the acidic strength will be better. So Ka2 of fumaric greater than Ka2 of malic. Right, student? I hope you understood this particular question also. Now let's move ahead. Now let's talk about the acidic strength of aromatic acids. Okay, aromatic acids, basically I'm having benzoic acid, right? Okay, student, if I draw the structure of this benzoic acid, can I see it's already a bulky group? Now if any bulky group is placed here, can I say it will face steric repulsion or steric crowding? Because of this steric crowding, what happens? This COOH becomes perpendicular to the plane of ring. C double bond OOH comes perpendicular to the plane of ring, right? And if it becomes perpendicular to the plane of ring, if it comes in this plane, obviously the planarity is lost, and because of that, now it won't be in resonance with the ring. Now this COOH will not be in resonance with ring, and this particular effect is referred as SIR effect, steric inhibition in resonance. Because of the bulky group, there is steric crowding, and because of the steric crowding, COH becomes perpendicular to the plane, the planarity is lost, resonance is inhibited. Okay, so what will be the impact of this SIR on acidic strength? Because of SIR, the acidic strength will increase. Why? Let's try to understand. Student, as soon as it loses its planarity with the ring, now I will have COH only. So this COH won't show resonance with the ring. Now I am going to remove the acidic hydrogen. So I will have C double bond O negative. Student, this is the conjugate. And now I will check the stability of this conjugate. Now this conjugate is having symmetrical and equivalent resonating structure. And if a compound is having equivalent symmetrical resonating structure, means a mirror image, almost similar, oxygen having negative charge, oxygen having negative charge, CW bonded O, CW bonded O, such a canonicals are referred as equivalent resonating structure or symmetrical resonating structure. And whenever we have symmetrical resonating structure, the stability of the compound is very high. Stability of compound is very high in case of symmetrical or equivalent resonating structure. And because if it is highly stable, the acidic strength will be very high. So student, now very important point. In case of benzoic acid, if any group is substituted at ortho position, irrespective of the nature of the group, we will experience ortho effect, and because of ortho effect, the acidic strength of benzoic acid will be more as compared to the meta substituted one and the para substituted one. I hope you understood it. Once again I am saying, irrespective of the nature of the group, whether it is a plus M or minus M, you don't need to consider. Only you need to check whether the group is substituted at ortho position or not, right? It's applicable in case of benzoic acid. Let's move ahead. Students, these are the general groups through which we will experience ortho effect. So if these groups are present, if I am having alkyl group present here, I will have ortho effect, and because of that, acidic strength will be very high. Now, one more thing, bulkier the group, more will be the SIR observed. Bulkier the group, more will be SIR, and more the SIR, obviously because of the SIR the planarity will be lost, and if the planarity is lost, I will have more equivalent symmetrical resonating structures or equivalent resonating structure. Because of that, the stability of conjugate will be more. So more is the bulkiness of this group, better is the acidic strength, right? I am having CS3 and I am having CME3. You tell me in which case I will have better acidic strength. Which one will have higher Ka value? CME. Because in case of CME3, I am having more SIR, and because of that, acidic strength will be more. Let's move ahead. Now we need to compare the acidic strength of few compounds. Student, this particular question was asked in JEE Advanced Paper 2016. Let's try to solve it. Carboxylic acid, ortho substituted carboxylic acid. Meta, so I will have plus I. Para position plus H plus I. Electron donating group will decrease the acidic strength. Here also plus H is there, but here this group is present at ortho, so I will simply write ortho effect. And if ortho effect is there, acidic strength will be maximum. So 2 max, then I will have 1, then I will have 3. This one is going to be least because here plus H group is there, and plus groups decreases the acidic strength, Ka value. Right? Let's compare this one. Just now I had told you, bulkier the group, more will be the SIR. I being bulky, here I will have more and more SIR as compared to Br and Cl. So acidic strength will follow this order. Right? I hope you understood this particular question also. Let's move ahead. Moving to the next question which we have on the screen, and this question is also really important, students. Please look at this question. I'm having ortho substituted benzoic acid, and here at ortho position I'm having OH group, 2 OH group. So where I will have more SIR? Ortho effect, here also ortho effect, but where I will have a dominant effect. Student, we say if OH is present, if OM is present, then we say ortho effect due to hydrogen bonding. And whenever we have ortho effect due to H bond, I will have better acidic strength. So if I compare between 1 and 2, 2 is going to be more acidic. Now between 1 and 3, here also ortho effect is there, but ortho effect due to hydrogen bonding, if OH, OMe, NH2, if these groups are present, acidic strength will be really high. Okay, so between 1 and 3, 1. And obviously here plus H and plus I will decrease the acidic strength. So the relative order will be 2, 1, 3, 4. Highly important questions. Please revise it whenever you are going to appear in an exam. Let's move ahead. Students, while solving the questions of GOC, most of the time we will see questions being asked like this. Which of the following acid will give effervescence of CO2 when treated with NaHCO3? Such questions are really typical questions of GOC and most frequently asked questions in all the competitive exams, whether it is JEE Mains, Advanced or NEET. Let's try to understand the concept hidden behind it. I'm having an acid HA and it's treated with a weak base NaHCO3, weaker base. Or right? It's also an acidic salt. And I'm having the formation of H2CO3. Along with that, I am having a formation of NaA, this salt. Although it's not relevant to me, for me, this one is important. Now, student, we have studied Le-Chatelier's principle, and it says strong acid always moves in the direction of weaker acid. So this reaction will be feasible only when this acid HA is stronger as compared to H2CO3. So all such acids which are stronger than H2CO3 will give effervescence of CO2 whenever treated with NaHCO3. Simply we need to check whether the acid is stronger or weaker as compared to H2CO3. Now let's try to understand it. So for effervescence, I should have Ka value of acid stronger than or larger than the Ka value of H2CO3. Okay, so which all acids will give effervescence? I will have squaric acid, then I will have picric acid. Squaric acid, if I write the formula structure, I can write it like this. Squaric acid, I will have picric acid. Although this picric acid is a much more stronger acid. It's not that I am writing relative order. It's simply all such acids will give effervescence of CO2 whenever treated with NaHCO3. I will have picric acid, then I will have this one also. Disubstituted nitrophenol, ortho, and as well as para. Even this one also. OH, NO2. Apart from this, I will have all the carboxylic acid, COOH, RCOOH, HCOOH. It's not the relative order I am writing. I am simply writing all the acids which are going to give effervescence of CO2 whenever treated with NaHCO3. Right? I hope you understood it. Let us move ahead. So that's it for today, students. I hope you thoroughly enjoyed the lecture, and this lecture will be really helpful for all your NEET revision as well as JEE Mains revision. No doubt we are left with a very important subtopic of this GOC, and that is basic strength. The comparison of basic strength of organic compounds. Highly important subtopic. But student, you don't need to bother at all. We are going to cover this basic strength in third lecture. There we'll be talking about basic strength and the reaction mechanism. Okay, so you don't need to bother. Lecture number 3 will start with basic strength, and then only we will move towards reaction mechanism. So I once again thank you all for watching this lecture.